Hello from Portland to the world. Is everything listening to the Nginsolve user meeting?
Okay, well, it's 9 a.m. So, welcome everyone to the NGSolve User Workshop, the first NGSolve User Workshop outside of Europe. We're very glad to welcome you all to Portland. So I'm going to introduce the main developer, Joachim Schobel, hand it over to him for a while, and then we'll do the tutorials. That's the plan for today. You had instructions up on how to download the tutorials before. So Joachim Schobel, most of you know him already, professor at Technical University of Vienna, with many fundamental contributions to finite element and numerical analysis. Many things named after him. Let's see. The Schobel Leonto ACD method was Leonto also the great Schobel technique for posterior estimation. Okay, so there's a long list. I don't have to tell you the long list. I think most of you know who he is. But he's also the main developer of NGSolve, which is an amazing piece of software. And if you don't leave this meeting in amazement, then we haven't done our job correctly. So I think you'll see most of the amazing features in this software which are not present in any other finite element software during this meeting. And this point will be proven right now in the next few minutes by just whetting the appetite that Joachim Schobel is going to present. Please.
Thank you very much, Jay, for this kind words at the beginning. So to give it back also, so Jay is a long-time best friend, cooperation partner, and you forgot to mention about the HP extension by Tinkovic collaboration. Jay did a lot of contribution for us, in particular for the documentation, to make it also accessible to people. So Jay is then giving the major part of the beginning of the tutorial. I continue, and Christoph Jernfeld, who is also a long-time developer since 20 years in Aachen, on some more advanced topics. Most of the topics for today are on unit square. And last time we started with the unit square, and people thought, okay, NGSolve is only about this unit square domain, and left already after 1 hour. So today we want to switch, start not with the unit square, but want to show some more moderate, impressive things you can do, hopefully for getting motivated into getting the simple stuff before then going to the more complex ones again. Okay. You may have this notebook also open on your computer or on a Jupyter Hub, and you can follow the notebook and click through the notebooks. Okay, I want to solve a Poisson equation first. Here's a Jupyter notebook. I'm importing NGSolve as a Python library. We have a unit square domain, which we can visualize here. You can rotate, okay, it's still flat. On this domain, we define now a function space, a overlap space H1, with boundary conditions. I'm going now very quickly over these notebooks, just to give an impression. We are solving the variational formulation, denoted by this, and you can write down this binomial form in NGSolve, as you can do it on paper. That is here the Python variational form language of UFL we borrowed and rebuilt in NGSolve. You can assemble. You have now the right-hand side vector and the matrix you can look at if you want to check the entries. The sparse matrix. You solve the problem with a direct solver, and you can plot the solution, you see here, with the visualization inside the Jupyter notebook. You can rotate it here. Here we have some simple controls. You can switch on edges or the wireframe or not. You can do also some deformation to see the solution as a graph. And you can draw also the gradient of the solution, the flux. You see small cones showing the direction of the flux of the computed solution. And finally we have a reference solution, and we can do something with the solution and integrate the difference between exact solution and error to compute the error. Okay, unit square example. There are some more interesting things. Let's do maybe pick a few. Now with Stokes equation, we're solving this equation for velocity and pressure. We have this flow channel with the obstacle in here. We model the geometry with the quite new open cascade wrapper to ng-solve. This allows you to model more complex geometries. Christopher will talk more about this open cascade. Mesh it. Do a simple discretization for the Stokes problem. Inflow. We have some term for time-dependent mass matrix. We have the nonlinear term of Navier-Stokes. So I'm just quickly going over it. If you know Navier-Stokes very well, you immediately see it, what is going on. Otherwise, I'm too fast, I know. And you can compute the time-dependent Navier-Stokes solution here. So I'm just computing here locally on the local computer. Oops. Some Maxwell magnetostatics example, so stationary Maxwell equation. So we are modeling a coil. There's a few lines of open cascade code for modeling a coil like this. So we model a helix here. We have some segments. We connect them C1 continuously to get this thin wire. Putting an airbox over it, and we are meshing it. Meshing takes now a small minute. You can look up here. So we have a cylinder. We give the helix in the parameter space of the cylinder. We have the straight segments here as line segments. We can give Bézier curves to give the control points of the spline to connect the curve C1 continuously. We have the circle as a phase, and we transport this along the curve. We also give names to the input and outflow of the wire. In the meanwhile, I got the mesh. You can look now at the surface mesh. So we have a volume mesh in between. Query some number of elements, number of vertices, material names we gave in the geometry. We want to send a current through the wire. For this, we solve a conductance problem, scalar potential phi, Poisson equation. We prescribe the current at the inflow and leave it open at the outflow. So we computed a scalar potential. You see it, so it's a potential follows the wire. And the gradient of the potential is the current. And now we want to solve a magnetostatic problem by using the current from the first problem as right-hand side for the magnetostatics problems, for the curl-curl problem. H-curl, if you want to read something about H-curl, get Peter Monk's book or ask him directly. Setting up the curl-curl problem. We have an H-curl space here and the curl-curl bilinear form. Now it's good to use a iterative solver, and the problem is already too large for the direct, or relatively large for the direct for my small computer. Iterating, and we computed now the magnetic flux, mainly localized inside the coil, these small cones, within the direction of the magnetic flux. And here the field goes along the wire. One more I want to show now is 3D elasticity, solid mechanics. We model this geometry here, so it's a box. It's a box. We're cutting out a few cylinders, so we have this holes here in the box. We can put boundary conditions to the faces of the box with minimal and maximal x coordinates, for example. I put some chamfer onto the edges here, so we have not that sharp corners anymore. This is done by this make chamfer function. Mesh it. You see the elements following smoothly to the geometry, so they are curved elements. We're solving linear elasticity, either you know it, or if you don't know it, you just look at the picture. We have a variational formulation like this, so we're looking for a displacement, vector valued h1 functions, x, y, z displacement, satisfying this variational formulation. We can write down it like this. Solve the linear elasticity problem. Do some iterations. did some post-processing for the mechanical stress. We can draw the displacement field, the solution. Here the web GUI is also very useful to open it. We can do a deformation and we can see how the object is stretching by scaling the force. And we can draw also the stress. And you see the stress mainly localized around the holes where it's most probably to break the solid. You can do also nonlinear elasticity. You can give a Cauchy-Green strain tensor. You give an energy potential. We use automatic differentiation to derive the energy potential, which allows a very simple implementation of Newton method. And we see how the beam bends nonlinearly, just by writing down the nonlinear energy functional, which is processed then by ngSolve. More on this in the afternoon on solving nonlinear problems. And the last one which came in just yesterday is if you have want to do some, for example, if you want to simulate a windmill or something like this, where you have a rotating domain, we can play also with, you have a mesh outside, you have a mesh inside, and I want to rotate the domain inside. This is two arms of the windmill, two holes. We can define a rotation function, a linear transformation which defines the transformation, and I can rotate now the inner domain. Of course, the mesh slides along the other mesh, and the meshes don't match, and we have to do something to make it conforming, to treat the nonconformity. We do this by Nietzsche's method, so which needs the integration from one side against the other side. Don't look at the details here. So since reason we can also integrate from one side to the other side. Here I'm solving a potential flow problem, also known as Poisson problem, where the Neumann boundary condition here is such that it compensates the mesh velocity, and with this mesh velocity we're setting up a transport equation where the total wind on the pulled back with the arbitrary Lagrangian formulation is the mesh velocity minus the potential flow solution, and I can now transport this peak over these non-matching interfaces. So the peak is you don't want to see the mesh. So if you don't see the mesh, then just the peak is rotating between the holes. But if you see the mesh, and you see how it is done, you solve on this rotating domain. We have the artificial mesh velocity for the wind, and the bubble is now exiting the rotating domain. For example, if you want to do a windmill, you want to have the subdomain of the arms of the windmill. Or if you do an electric machine, you mesh the rotating part, mesh the stationary part, and you have to conclude together the fields at the interface. Okay, so far some few recent, older, more recent highlights of ngSolve, and I hope this gives some motivation to look into things more detailed. We continue now with some simple things, mainly staying on the unit square, how to work with rational formulation, spaces, trial test functions, how to set up the problem, what you can do. Hope you are motivated now in working with us through the tutorials. So hopefully you can run these examples now on your computer or one of the Jupyter hubs they're providing. I would say we have a 5-minute break. If people have not set up the Jupyter notebook locally, they've now got 5 minutes time to get it running with some help maybe from Christopher or others. If you don't think you get it on your 10 years old laptop, then use the second Jupyter hub, go to this address, use this password, then you can follow the tutorials. Somewhere, that's how we go over it. Let's do 5 minutes breaks before the start with
Alright.
tutorials.
There should be coffee up there, and if you haven't taken your bathroom,
Feel free to ask questions now, or you can ask questions also in the chat, and people around here can help in another chat. Think how it's quite appropriate to ask questions. So maybe you can explain more concepts if you ask directly, or if some small technical things then. Okay, let's
all right.
start with the first.
So these are getting started tutorials, and so we will go somewhat slowly through the first two, but then I only have a certain amount of time, and there's a lot of things that must happen within that time, and I don't want to take time away from other people who have very interesting things to say. So I'll speed up a little bit after the first two, and so feel free to stop me anytime. But I want to say the intent when we get into some of the later tutorials is just so to tell you what is in here that you can go and look up later. It's okay if not everything is comprehensible in these short 10-minute tutorials, but if you carry with you a note that in these tutorials, in this place, I can find this whenever I need it, then that's the purpose of the tutorials. So we'll start with 1.1, which is a rehashing of what Joachim did in 30 seconds at the beginning, but a little bit more slower. So resolving the first problem in any finite element course, Laplacian equal to a given source with some boundary conditions. So here we have the domain set to the unit square, and the bottom and right parts of the boundary have Dirichlet conditions, essential boundary conditions, and on the remaining parts you have Neumann boundary conditions. Here's a quick rundown of steps to the solution, typical workflow in ngSolve. You first import everything from ngSolve, or import what you like. If you already know the package well and you know what to import, you just import what you need. And then after that, you generate a mesh. And you can draw the mesh and query the mesh for the number of vertices and number of elements. You can draw the mesh here, and the web GUI will show you a picture of the mesh. And as you've seen in Joachim's Whetting the Appetite, you can move things around, examine it closely. If you can zoom in and you can open the controls, and there's more stuff here. And if you're frustrated by the fact that the controls are kind of looking too small, you go to full screen, and then you have more space to look around in the controls. Right? You can adjust things. Okay. That's the mesh. Now, how do we solve the problem? We declare a finite element space. Everyone who's taken a finite element course knows what this thing is, H1. And we're not equipped to talk about what H1 is at this point, but we'll just use what is called H1 in ngSolve, which is the Lagrange finite element space of the input order together with boundary conditions. So you have to specify which part of the boundary should question over there, I think. Somebody needs help? No, okay. So by this flag, Dirichlet flag, you're specifying what parts of the boundary should get the Dirichlet boundary conditions, or the essential boundary conditions. And you can query the number of degrees of freedom of this finite element space, and we'll talk more about this and how the boundary conditions affect this degrees of freedom or not in later tutorials. And you can of course always type help on an object in ngSolve, and most objects now should have some documentation that comes up in the form of Python's online documentation. As you can see, the finite element space has a lot of functions, and you get member functions and data attributes, and you get information on all of that here. Okay, to solve the problem using this finite element space, you declare a trial function and a test function from that finite element space. So this is the finite element space we created, and these are methods of the finite element space. They give you trial and test functions, and the difference between trial function and test function and a grid function is that a grid function has memory to store a solution, whereas a trial function and a test function are just symbolic objects that you use to declare a problem or a bilinear form. Okay, and if you become more conversant, you don't have to write this trial function and test function laboriously. You can do fancy things like this one-liner, where you get both U and V together in the trial and test, or T and T. Nothing to do with T and T. But okay, here's how you declare the bilinear form. If you want to solve the Poisson problem, and you saw this in Joachim's Whetting the Appetite also, we make an integral of gradient of U against gradient of V, and this is how you specify the form. Okay, and as we go further in the tutorial, you'll see that you can do these three things in one line. Okay, but you have to wait for that. Okay, and here is the right-hand side. The right-hand side is X in the PDE, and you're multiplying that with the test function and integrating. And the assemble gives you both A and F. And here's the one-liner that I told you about. So instead of writing all of this, now you can just do gradient of V, star dx, and then dot assemble, and that does the whole thing. Okay. Now, if you want to examine the system, linear system in that we just assembled, that we can ask to print out the vectors. You can ask to print out the matrices. So these are the entries of the right-hand side vector. It's a lot in there. Here is the matrix. Okay, the matrix is is printed out in a CSR format of a sparse matrix. Okay, it goes on and on forever. We don't need to see all these numbers. Okay, we need to solve the system. To solve the system, you ask the assembled matrix to do the inverse method. The inverse method essentially inverts the matrix. Okay, and once you invert the matrix, you need a place to store the inverse multiplied by the right-hand side, and this is the grid function we created earlier, and we are assigning to the grid function the inverse multiplied by the right-hand side, and then we are asking to draw the grid function, and here is the solution. You can see the Dirichlet boundary condition being imposed in these areas, and you can ask in more detail what precise degrees of freedom are being constrained by the Dirichlet boundary condition and so forth, and we'll delve more into that in the next tutorial. And you can certainly print the entries of the solution vector if you want to think of it as a linear algebra object. Okay, and I should also mention before we conclude this little tutorial that there are many ways to interact with ngSolve. What we're doing is via Jupyter Notebook. You can also write a simple Python script and run the Python script by itself. And and then you would call the Python script using as usual. And if you want a GUI, a Netgen GUI that stands by itself without any reference to a web browser, then you run the program or run the script that you wrote using Netgen instead of Python 3. And from the Netgen GUI, you can get a Python shell. There's a button there that the solve. In the solve menu, you'll see the Python shell button. Okay, so any questions?
Totally random question. Is it NetGen or NetGen?
Oh, ask the guy sitting next to you.
I say NetGen, also say NetGen, so
it's like
everything is
French. It's like GIF. Thank you.
All right, so we'll go back to the index and to the next tutorial, number 1.2. And again, we will take this a little slower than the other tutorials because there's a lot of stuff that if you haven't used ngSolve before, there's a lot of stuff here that is very useful for dealing with the software. So the coefficient function is central in ngSolve. They are representations of functions on a domain, or a domain after meshing. The mesh object is what you saw in the previous tutorial. Once you have a mesh object, you can define coefficient functions using the coordinates x, y, z, and so forth. And the coordinates themselves are coefficient functions. So we will see a lot of things related to the coefficient function in this tutorial, like defining, visualizing, evaluating, and then we look at the expression tree of a coefficient function to know how it's internally stored, and that then allows us to do things like optimization of evaluations of the coefficient functions, or at least understand what the commands to optimize do. And we can integrate, differentiate, we can include parameters that change later in some stage of the computation, interpolate, etc., etc. So let's begin. Let's begin by creating some mesh. Here is the unit square mesh, a mesh of a unit square. And here's a function. It's the definition is transparent. It's x times 1 minus x. This object x was imported when you from the first line. When you say from ngSolve import star, it imports a lot of stuff, and x and y are imported that way. And you can wonder, what is this x and what is its data type? And you see that they're all coefficient functions. So x is a representation of the first coordinate as this object coefficient functions. So certainly, if we want to build functions out of x, we need to understand what this coefficient function is. So here are things you can do with once you declare a function. You can ask it to be visualized using the draw command. You can ask it to be evaluated, provided you have a mesh. So the mesh knows how to evaluate a coefficient function. So you give you want to evaluate this function at the point x equals 0.2, y equals 0.2. You give that xy coordinates to the mesh. It then returns an object called a mapped integration point object, which can be passed into a coefficient function, and it'll evaluate the coefficient function at that point and give you a number. Okay, this is a usual mistake. Sometimes I do this too. Instead of doing this mesh, you put in the xy coordinates right there, and nothing happens. Okay, so you have to first use the mesh to get a mapped integration point, and then pass that into the coefficient function. Okay, and you can not only evaluate the function at a single point, you can evaluate it at a set of points. So here's a set of points. You make a list comprehension of a number of points, say 11 points here, and then pass it to this function, and you get a list of values. And for example, you can plot this set of values or print out this set of values. Here we're printing out the value of this function at a number of points. Okay, now if you have 100,000 points that you want to evaluate, if you do this list comprehension, it's going to be slow. So you want a vectorized version, and here's a vectorized version. The vectorized version using NumPy creates the array in one shot, all the points that you want, all the x coordinates and the y coordinates in one shot, and then mesh xy then gives you a whole. We're not printing out this list, and that can be passed to the function, and it'll give you the whole list efficiently as a NumPy array. And you can plot this set of values of a function. Remember the function that we're dealing with, my func is x times 1 minus x. If you plot it, it's going to look like this. Okay, now for the representation of coefficient functions internally, if you print a coefficient function, you will see a printout of an expression tree. So let's look at this here. Here's x times 1 minus x. This is being parsed as a tree. At the top of the tree is the star operation. That's this operation. And the star operation has two leaves. One evaluates x and the other evaluates 1 minus x. So the evaluation of x is right here. The evaluation of 1 minus x is another tree rooted at minus with 1 and x. So that's 1 minus x. And so you see the tree structure. Now you give it a complicated expression, I will not be able to parse the tree, but you can sort of see how this works. So when we say evaluate a coefficient function, it's traversing the tree and evaluating every node of the tree. Okay, and we'll come back to this tree business in a second. But let's see other things that are useful things for a finite element person. Integrate a function. Okay, here's how we integrate. And when you say from ngSolve import, it imports this integrate thing, and you can integrate a function over a mesh, and you can specify the order of integration, or the order of quadrature you want to use. Okay. You can differentiate. Differentiation is done via automatic differentiation. Automatic differentiation is a symbolic process. So let's differentiate the function x times 1 minus x, and the result of the differentiation, if you look at it, it does not look quadratic, it looks linear, so probably did the right thing. And we can actually see what's going on in the implementation if you print out the tree of the differentiated function. So this is what is actually implemented. So the product rule is implemented. And so when you have an expression like this, which because it's a tree containing the star, the differentiation process, the product rule is being implemented. And if you look at the tree carefully, then you'll see that the elements of the product rule here. You see this expression, there's a plus here, so the tree begins with a plus, and these two are the leaves of the tree. And the first leaf here has dx over dx, which is 1, and 1 minus x, and you should be able to see this. I think you see it here. 1 and 1 minus x. Okay, so if you look at it slowly, you'll see both parts of the. This thing is supposed to give you a minus 1 times x, and that's you see scaling by minus 1 and x. Okay, so that's you get an idea of what is being done in the automatic differentiation procedure. You can introduce parameters into coefficient functions. So y is a coefficient function, sine y is a coefficient function, sine of ky is also a coefficient function. The only difference here is that k is declared to be a parameter, which means that you can use this coefficient function with one parameter, and later on you can change the value of the parameter, and it's it knows how to change the evaluation process. Okay, here is sine k times y, more or less looks like a sine. And you can later set the value of k to 10, and then you see that also looks like a sine of a higher frequency. And if you look at the expression tree of f, you'll see the parameter that we call k appearing as this thing. So the parameter is a node in the tree, and you can differentiate with respect to nodes in the tree. So therefore, you can do f. You can differentiate f with respect to either y or with respect to k, and you can verify that. While if you're an expert in reading trees, you can verify this. It's going to take me a while to get into what this tree is. But alternately, you can see if you get the right answer by doing tricks like this. Here's the derivative, and we know how to differentiate. So we make sure that it gave you the right answer by taking the difference and verifying the difference is 0. Okay. The other important thing to do is to interpolate a function into a finite element space. Okay, so a coefficient function, my func, is not the same as a grid function. The grid function is an object which has memory and it represents a function in a finite element space, but you can interpolate a coefficient function into a grid function, and that is done using this operation called set. Okay. Set is synonymous with interpolate. The set actually what it does is a particular type of interpolation that first zeros the grid function, then projects it element by element in the L2 norm, and then you get a piecewise polynomial that's discontinuous on the mesh, and then you average the degrees of freedom to bring it back into the finite element space you're doing the interpolation. Okay. Fancier ways to do interpolation, I think Joachim will probably talk about it in chapter 2. Okay, so vector valued coefficient functions. So far we've seen scalar valued functions. A vector valued coefficient function, you just have to give a tuple as an argument to coefficient function, a tuple with x and y coordinates or x, y, and z coordinates. Okay, so here's a vector field. And if you're already getting tired of writing coefficient function, then you may write CF. Okay, that's and you can picture the vector function. And in order to picture the vector function, there are arrows. These arrows came up in whetting the appetite on more complicated domains. But you see the arrows are colored, and they're colored according to the magnitude of the vector. And the arrows show the direction of the vector. Okay, here's another example. You can take a scalar function and then take its gradient, and you get a vector function. And you can ask, how does the gradient of a vector function look like? So a gradient of a Lagrange function is a piecewise constant vector field. So you see that the magnitude of the vector is a piecewise constant function, and I have put a lot of arrows here by prescribing that it should be plotted on a grid of 30 by 30, but I can't see it here. Okay, I think you can see it there. Okay. Yeah. Oh, okay. So just to point out, you can this vectors equals true argument will plot the vectors, and you can tweak it and provide further options in this dictionary, asking you to plot on finite grids and so forth. Okay, now we come to evaluation of coefficient functions, or making the evaluations faster. You can make the evaluations faster by compiling the tree. Okay. Here's how you compile the tree. There's a compile method. But to understand what is happening behind the scenes, we have to look at the difference in the internal structure of the tree-based form, which is the structure we saw before, and the compiled form. The compiled form does not look like a tree. It's a sequence of steps. So what happened is the tree traversal has been transformed into a sequence of linearly ordered steps. And if you want to read this sequence of linearly ordered steps, for example, step number 2 is a binary operation. The operation is minus, and the operation is being conducted on 2 inputs, 1 and 0, but it's not 1 minus 0. It should be interpreted as output of step 1 minus output of step 0. And similarly here, star, it's output of step 0, star, output of step 2. Okay, so the tree has been converted into a linearly ordered sequence of steps, and that's usually faster to evaluate. It's particularly fast to evaluate if the tree has a lot of repeated nodes. So here's an example, cooked up example of an expression with a lot of repetitions, and you'll see the difference in the evaluation times. Instead of evaluation time, evaluation time is very small, so an integrate requires the function to be evaluated at all the integration points, so we are using integrate to measure the time. So that takes, what, 486 microseconds, and if you look at the compiled form, hopefully it'll take less, about 10 times faster. And if you're working with an ngSolve that's built from source instead of a binary install, then you have a compiler script that came with your build. So in that case, the following line will succeed without an error. Otherwise, you might get an error. And that, what it's doing is this linearly ordered steps. It's actually sending it to the compiler, to the C++ compiler, with all the options, the same options that were used in compiling ngSolve. And that should give us a little bit more speed. Okay, reduced it by maybe half. Compared to the so if we didn't do anything, it was 486. If we did the compile, it's 44, and if we did the real compile, then it's 28. So these experiments will give you an idea of how to make the evaluation of an expression tree fast, and you can also look at the trees if you're adventurous. For this expression, the compiled expression has 25 steps, but the tree is really horrible. Okay, well, okay, but I'm not going to parse that. So, okay, there we are.
I was just going to ask, what's the order in integrate? What does that mean?
Order is the order of the quadrature. Integration is done by a quadrature rule on elements. And you can have high order quadratures. You can omit the argument and it'll do some default order. But if you suspect that in some element there's sharp variations, you might want to increase the order.
Nice. Okay.
Questions?
Question: in the time bit, what this loops each? What that means?
Let me go back. What's that? Oh,
like 10,000 loops each.
To get reliable timings, time it does the same integration 10,000 times, whatever it said. So it did the integrate 1,000 times, and then average the result to get the.
And then the next one is 10,000.
Because it was a shorter time, so it did more of it. Microseconds, yeah. Okay. Any other?
If you create your own coefficient function and you want to give it a derivative,
Yeah.
Sorry,
No.
You want to give it a derivative, you just have to be like, this is the coefficient function derivative.
The derivative, it computed it. But
I mean, if you were to create your own, like, I know there's various ways to set up your own coefficient functions. You just have to know what it is.
Yeah, very good point. Yeah. For example, you want to make your own sinus function or some Bessel function or so. You have to provide what is the derivative of this. You have to provide that the derivative of sine is cosine.
As another coefficient function.
Yeah.
Okay. Yeah. Cool. Not numerically, I guess, is what I mean.
yeah.
Symbolic, right?
Yeah. An expression involving sine, ngSolve already knows the derivative of sine is cosine, but I don't know if ngSolve knows the derivative of the error function or Bessel function. Yeah.
Luckily, that's just the error function derivative, just the
We know error
You
function.
can provide.
yeah.
If it's a commonly known special function, you probably could do it in some other, like in SymPy or something, and then evaluate that in ngSolve, and you would be able to get a coefficient that way.
C++ keyboard for Bessel function is in ngSolve now.
Oh.
Oh, is it in ngSolve itself, or is it in?
Special coefficient. ngSolve.
Not special functions, but special
Yeah,
functions.
yeah.
Okay.
There is a GitHub page. I think it's called NGS Special Functions, which provides an add-on module for containing special functions.
It's with Fortran implementation of about 5,000 special functions.
Yeah, this is the same thing.
And this runs also in parallel. When we integrate in parallel, then the call to this function goes also in parallel. But yeah, would not work for a sci-fi.
Okay, so we go on to the next tutorial, 1.3. Okay, we want to go a little bit deeper into the mechanics of how Dirichlet boundary conditions are imposed in ngSolve. Okay, so here's the idea. It's what we learn in finite element textbooks. If you have non-homogeneous Dirichlet data like this on a part of the boundary, we extend the Dirichlet data from the boundary parts into the interior of the domain and convert the boundary data into a volume source, thereby reducing the non-homogeneous Dirichlet problem into a homogeneous Dirichlet boundary condition problem. Okay, and then we'll discuss what is happening in the homogeneous case. And of course, there is we will look at these steps, these first three steps in detail. And if you don't care about all these details, and you just want to get the thing done, then you just go directly to the end of the tutorial, and there is an automatic utilities, it's something like solve BVP or something, and it'll do it for you. But if you want to understand what's happening behind the scenes, you look at these three steps that I'm going to explain now. Okay, so again, our famous unit square. It has four boundary parts: bottom, right, top, and left. And suppose we want to impose non-homogeneous Dirichlet boundary conditions on the left and right. Okay, so first we declare that, let it be known to the finite element space that left and right are going to be Dirichlet boundary segments. Okay, and now there is a point of potential confusion. Here's a space where there is the Dirichlet flag set, and here's a space without any Dirichlet flag set. So you would think that the number of degrees of freedom of these two spaces are different because one has Dirichlet boundary conditions and the other doesn't. But if you ask for n DOFs, or the number of degrees of freedom, you get the same number, and then you are upset. And so you should not be, because the way the Dirichlet boundary condition is imposed is through another facility called free DOFs. Okay, free DOFs says what degree of freedom is free versus constrained. When you have a Dirichlet boundary condition, at a certain point, then that point is constrained to have only the values the Dirichlet boundary condition allows it to have. So that's a constraint node. When it's not constrained, it's free. Okay. So the number of free DOFs, or this entire array of free DOFs, you can print that out. And if the print looks a little funny, you have to this whole thing. The first three lines is one vector. So we're just printing zeros and ones as a bit array, but only 50 characters are printed per line. So these three together makes one bit array. Okay, and as you can see, the FS2 space, where we did not set any Dirichlet boundary condition, has all degrees of freedom free. The other one, FES, where left and right was set to be Dirichlet boundary condition, you have a bunch of zeros there, indicating that some of these degrees of freedom are not free, or they have Dirichlet constraints. Okay, so this free DOFs is important for how the Dirichlet boundary condition is implemented. The next thing is the extension of boundary data. So if you're given a G that's supposed to be the boundary data on the boundary, we have to extend it inside the domain and as this function, U sub D, the extension of the Dirichlet data, and then write the original solution as something with zero boundary conditions and this extension. Okay, so once you do that, you plug this back in to here and move the data, Dirichlet data, to the other side, and you just need to solve a problem with 0 Dirichlet boundary conditions. Okay, so in order to implement this approach, we need to know how to compute U sub d. That's the first question here, and then the next point is how do you solve this for this 0 Dirichlet boundary condition problem. Okay, so the first point about how do you get the extension. Suppose we're given a data like this, sine of the y coordinate. Okay, and we want to set this. We want to create an extension. The same facility we saw before called set gives you an extension of this boundary data. Okay, so we take a grid function and we set this grid function using this sine y, which is a coefficient function, but now we say that set it only on the boundary. So this is different from the set we saw before, in that we provided this argument. And then when you draw this function, you see that the values of sine y has been imposed on the boundary, and this extension function is cut down to 0 in a strip of elements adjacent to the boundary, because all of these blue areas are 0. Okay, and the keyword B and D is what tells it to do that, to just set the coefficient function on the boundary and then cut it down to 0 in this one strip of elements. Okay, now so we did the extension. The next step is to solve for the problem without any boundary conditions, now that we know the extension. And for that we make the bilinear form, and then we look at how do you compute this U0. So one way to understand it is to separate the degrees of freedom into free and Dirichlet constraint degrees of freedom. Write up the matrix, partition the matrix using these indices corresponding to free degrees of freedom and the Dirichlet degrees of freedom, and then write this equation down, or this equation down in this block partition form. And what we want is this thing. This is the values of U0 at all the vertices where its value is not 0, and from this equation you can solve for that, and that's what's happening here. So you compute f minus ud, which is this thing, and then you have to do the inverse of f, but only on the free degrees of freedom. So you need a way to say that don't try to take the inverse of this whole thing, but just do the inverse on the free degrees of freedom, and the syntax for that is coming below after we make this right hand side. Okay, now we have this modified right hand side R, and taking this inverse in the free degrees of freedom is accomplished by this, by providing an argument to the inverse, to ask the inverse to do the inverse considering only the free degrees of freedom and ignore all the constraint degrees of freedom. Okay. Okay. So once you do that, you have the solution, and you can do all of this all at once using this BVP facility inside the solver's submodule. All you have to do is to provide it with a bilinear form, the linear form, and some sort of preconditioner. You could give any of the ready-made preconditioner, and that'll do. Okay, questions?
Don't forget the plus equals, because I think that's one of the most common mistakes in this, that you forget to add it to the Dirichlet data, and I very often see an equal here and then.
Yeah, you've answered a lot of forum questions on this.
Can you do me a favor and deform the solution there for a second?
Deform the solution? Okay.
Because I'm curious, and this has been a thing I think Dow told me, which is that it appears where you haven't otherwise set Dirichlet conditions or interpolated something, you have Neumann conditions as default.
Yes.
Is that the case? And is that the case for every space, that there's some, when you're not doing Dirichlet, there's some default condition?
Yeah, so this is another finite element question. So when we integrate by parts and make the variational formulation, the Neumann condition is in the variational formulation. It's a natural boundary condition. So if you don't do anything, that's a natural boundary condition that is imposed.
I see. So if you tried to catch that, you'd have to do boundary things in your bilinear forms and stuff.
If you have a non-homogeneous Neumann data, then you would need an additional integral.
Yeah.
If there is no additional boundary integral, you're just doing du dn equals 0.
I see.
Already in the finite element space, you say this as a Dirichlet boundaries. There you have set constraints.
Yeah, we don't say Neumann equals this. We only say Dirichlet equals this because only the essential boundary conditions are to be imposed in the space. Any further? Okay. Am I going too slow or? Okay, so the next topic is static condensation. Okay, this has some long linear algebra formulas, which you can stare at them and be happy, or you can work it out. Maybe there's not enough time in this tutorial to work out those formulas, but you know that they are there and you can return to that whenever you want to. Static condensation refers to the process of eliminating unknowns that are inside an element and don't talk to other elements. Okay, so they are useful for standard methods, but some people here are experts in HCG method, and they are critical in HCG methods. Okay, so the purpose of this tutorial is to show you how to turn on the static condensation, and it's done by one keyword. The keyword argument is condense. Condense equals true or false. And then to understand what's happening behind the scenes, there is this long linear algebra formula, which has multiple pieces, and these pieces are all available in NGSolve as data attributes of a bilinear form. And these are the attributes: harmonic extension transpose, inner solve, and we'll see what all of that are in a second. And all of these help us do a Schur complement factorization of the inverse. And then we'll see how does NGSolve know to do this type of factorization. It needs to know the block partitioning, and the way that's implemented is using this data type called coupling type that divides an unknown in a finite element space into a category of local degrees of freedom or coupling degrees or not local degrees of freedom. And as usual, there is an automatic utility if you don't want to see all the steps, but you can call a one-liner that'll do it for you. Okay, we start with the unit square again. Okay, this time we'll take the usual Poisson bilinear form and ask for condensation to be turned on by this keyword argument. Okay, so this is the one-line syntax where you assemble where you symbolically make the form and assemble it, and all of that happens at once. And here's the linear form, and we have a grid function. Okay, now we can think of this assembled matrix as block partitioned into local degrees of freedom and the remaining, which for this purposes we'll call E, or interface degrees of freedom. Okay, so we have the LL block, the LE block, and the other blocks. Okay. Just a block partitioning the matrix. So in the Lagrange finite element space, this E consists of edge and vertex degrees of freedom, whereas the L consists of the degrees of freedom that are interior to a triangle. So for example, in a cubic finite element, there's one degree of freedom that's interior to a triangle. And that'll be all of those, one per element will consist of this index L. Okay, and this is the Schur complement. You may have seen this from linear algebra. When condense is set to true, what happens is that the meaning of A dot assemble changes. A dot assemble does does not produce the entire matrix A, but it produces this matrix with a lot of zeros and the Schur complement. Okay, so if you print out the A dot mat, expect to see S. And if you try to take the inverse of this, then you're not taking the inverse of A dot mat dot inverse, you're taking the inverse of the Schur complement of this matrix. So that this is, of course, there's zeros there, so you ignore the zeros and take the inverse of S, and it takes the inverse of S and pads it with the sufficient amount of zeros to get the same matrix size. And that's turned down by this flag. You look at trade-offs, and you pass into trade-offs only those degrees of freedom which are coupling degrees of freedom, the interface degrees of freedom, excluding the local degrees of freedom. Okay, so this statement does not take the inverse of the matrix A, but it takes the inverse of the Schur complement. Okay, how is that useful? Of course, we want to invert this matrix. The inverse of this matrix has this form. This is the factorization I was mentioning. It's a factorization into product of three matrices, and the inner matrix has this Schur complement inverse, which we made. So if we can make this and this and this, then we can implement this formula, and that's the static condensation formula. Okay, so how do we make these things? Well, these things are essentially provided to you. This matrix is provided to you inside the harmonic extension transpose. The other matrix, the one over here, is provided to you in harmonic extension data member, and this inverse is provided as the inner solve attribute of the form. Okay, so getting the full solution from the condensed system, therefore, is just a matter of implementing this formula. And here is a way to implement this in a newfangled operator notation that is now pervasive in ngSolve tutorials. In order to make, we're given this as the harmonic extension, and then we pad it with the identity matrix. That step is right here. This is the extension. The identity matrix plus the harmonic extension gives you this matrix. This thing is the harmonic extension transpose. Add to that the identity matrix, you get this matrix. And then you have to compose all of these three matrices together, and that's the operation here. It is this matrix composed with inverse of S without this component, composed with this, that's extension transpose, and then you add back this part that was left out, that's the inner solve. And that's the representation of the inverse of the matrix using this Schur complement factorization based on local degrees of freedom and interface degrees of freedom. And you can take that inverse and multiply it with the right hand side, and you get the solution. Okay, no questions? I can proceed. Yeah, question.
I was just going to note that looks like a lot of new things for the harmonic extension trans. The attributes have exploded recently, because I was hoping at one point to take the adjoint of one of them, and I couldn't do it previously, but now it's in here. It's really useful.
You can tag somebody.
Yeah, thank you for doing that. That's awesome. That's going to save me some of our code. Yeah.
All right.
I hope useful things are coming in then.
Because previously it had been kind of a C++ mystery somewhere. It's like, I don't know what this item is quite.
Yeah.
Not very clear.
Yeah, so some of the new things are built into the tutorial, so it's a way of disseminating the new things, and some other things are still remain secret.
Well, yeah, keep your secret.
Until the next user meeting, maybe.
There's always a decision what is made visible to the users and what is hidden in the PVP function. So I like to show it to people what is done behind the scene.
Yeah.
Of course, it needs some explanation and maybe.
few more words of explanation before we quit this tutorial. In order to compute these things, it needs to the ngSolve needs to know what is L and E, which is this in this block partitioning. There were these index sets L and E, and the way it knows that it's important to know the way it knows that because it's a unified framework for all finite element spaces, not just the Lagrange finite element space, and the implementation is using this coupling type. So if you take any finite element space, you can ask the finite element space to tell you the coupling type of every degree of freedom it has, and it's going to print out a whole list of things. And you see there is something called the wire basket degrees of freedom, etc., etc., and then interface degrees of freedom, etc., etc., and then local degrees of freedom. Okay, so we at least saw 3 different degrees of freedom types. I think maybe Christoph Lehrenfeld will talk about other types of coupling, right? Hidden degrees of freedom? No? Okay. Okay, that will remain hidden then. So in this example, we have 3 types of degrees of freedom: local, interface, and wire basket. And every finite element space in ngSolve has such degree of freedom classification. So if you are taking the source code and you're making a new finite element space implementation, you are required to provide this coupling type of each degrees of freedom. Okay. So what it's doing? So now that the what is marked local degrees of freedom is the index set L, and everything else is in E. In our previous formula, that's how the factorization is implemented when condense option is turned on. And so you could do condense on any bilinear form on any finite element space as long as you have arranged things so that this block ALL is invertible and the Schur complement is invertible. Okay, now here's things get complicated when you mix the Dirichlet boundary condition stuff in the previous tutorial with the static condensation, and so this is just there for your reading pleasure because I'm not going to explain this. And you will stare at this very nice terse little code and wonder what is happening here, and then after some minutes you will realize that it is the correct expected thing to do. But okay. And then there is the automatic facility where if you don't want to think, you just want to solve the problem, get it done, and you just call the solvers module and do BVP and provide it with the bilinear form, linear form, etc., etc., and out pops the same solution. Okay, it's printing out the error just to check that we've got. In this problem, the error should be machine 0 because the exact solution is in the finite element space. Questions?
Sorry, I'm asking a question after every single one, but is it fair to say like a wire basket DOF is like kind of like a vertex degree of freedom is shared between more than 2 elements? In the Lagrange finite element space, that's a good way to think about it. We'll see another. We can actually tweak wire basket degrees of freedom by redefining the coupling degrees. So you might say I want the edge to be a wire basket but it's
fair to think of things like
yeah.
It's not always the case, but in the summer case it is.
It'll come back in maybe in 2.1 or something. We'll see that again. Other questions? All right. So tutorial 1.5 is on spaces on these region objects. The region objects in ngSolve are either subdomain regions or boundary regions. Both are region objects, and it's good to know about them because you can do operations with regions that are often useful for complicated domains, and you can integrate on certain regions and you can compress finite element spaces if some regions are not of interest and so forth. So this tutorial is devoted to those topics. Okay, so now instead of the unit square, we have a rectangle. We're making progress. So, okay, it's a rectangle. Yeah, yeah. I'm sorry. It's this rectangle is a square, so don't get excited. You're right. Yeah. Okay. There is a real rectangle in there. So we're making an outer rectangle using the OCC, or Open Cascade, and we're marking. There's going to be a longer tutorial on OCC tomorrow.
Do as much as you want. I skip the parts.
Okay, right. Okay, so so you'll see the syntax for OCC. There's documentation on that online also, and you can name the edges of a rectangle by pointing at, for example, like this. It says pick out the edge which has a maximum x value and call that right, or R. Pick out the edge which has a minimum x value, call that left. And similarly, bottom, top. And then draw another rectangle inside, and you do that by moving the point to wherever you want the other rectangle to start, and describing the dimensions of the rectangle. Okay. And here this rectangle is going to be submerged inside the outer rectangle. So there's going to be an interface inside the element, and that is inside the subdomain, inside the outer subdomain, and that's called interface. And if you want to think of the inner rectangle and what's left out by outside, well, then you have to subtract the inner domain. So the outer domain is now after the statement, the outer domain does not contain the inner rectangle. Okay, so picture does more than all the explanations that I just said. Here's the inner rectangle, and here's the outer rectangle. Okay. So that's how we make a very simple domain in using the Open Cascade geometry, and then we can mesh it. And you see the mesh respects the subdivision that we laid out. There's an inner rectangle and an outer rectangle, and they are different regions in the same domain. Or we like to think of it as subdomains. These are two subdomains, inner subdomain and outer subdomain. And if you ask for the type of this object, the subdomains, you can think of them as materials or material subdomain. Then mesh.materials inner gives you an object that you see is a region object. And you can do this a similar thing for the boundary. We mark the boundaries as bottom, right, top, and left. And if you look at mesh boundaries B, you see it's also a region object. So both boundaries, parts of the boundary, and subdomains, they're all region objects. Okay, now here is an example of a finite element space defined only on a subdomain. Okay. We say that there should be a Lagrange finite element space defined only on the inner rectangle. Okay. And you can construct grid functions that belong to just that finite element space, so you don't have to, the values outside don't participate in any computation using this finite element space. Okay. The next point is about the number of degrees of freedom. If you have a finite element space that's on the whole mesh including the inner and the outer subdomains, and you have the finite element space that we built before, FES1, which is defined only on the inner, you would expect one to have significantly less degrees of freedom, but the end-offs does not reflect that. Okay, so we need to know what is happening behind the scenes. It's the same business that we saw in the Dirichlet boundary condition implementation. You're constraining some nodes using the freed-offs. So if you print the freed-offs of the inner subdomain, you will see that a lot of the nodes, a lot of the entries in this bit array are 0. There's only 1, 2, 3, 4. I can't count it. Sorry. There's a handful. There's 2 handfuls of freed-offs, and everything else is unconstrained. Okay, and you can also understand the same information by printing out the coupling type. You see the wire basket degrees of freedom we saw before, you see something new called unused degrees of freedom, and you see, well, that's it, unused degrees of freedom. Unused degrees of freedom are the degrees of freedom that are falling outside the inner region. And it's possible to remove this degree. If you wanted to do some computation involving only this inner subdomain, it doesn't seem reasonable to store this lengthy vector of degrees of freedom, both the inner and the outer. So you can ask the finite element space to be compressed so that grid functions from that will only have degrees of freedom corresponding to the inner subdomain. And then you see the right number of end nodes after the compression. You can integrate on regions, and this is more or less as expected. What you need to know is this syntax. You can, when you integrate using dx, into dx you can pass an argument. You say that this volume integration should only be performed on a region. And how do you specify the region? You specify it using mesh.materials and give the region name. And similarly, you can ask for integration only on a part of the boundary, and like for example, only the top part of the boundary, and that's how you do it. So we've just made a source term that looks like a sum of two integrals, one using U1 and one using the top boundary. Okay, I should mention that if you look at the documentation of dx, you will see this. Look for this optional union of a string and a region object. This means, okay, where is it? You see it here, optional union. This means that you can, instead of giving this object, which is a region object, you can also just give it the string, and it knows to extract the region object from it. So you might, instead of writing this lengthy expression, you might as well have written this dx with a string inner. Okay, we can solve a problem, and then we can look at the problem, and you look at the solution, and you see well, something happening in the inner region. Okay, operations with regions. So, given any mesh, you can ask for a list of all boundary regions. You can ask for a list of all subdomain regions. This is how you do it. Get boundaries. You see that there is four edges named interface and another 4 edges named bottom, left, right, top, and so forth. And here's a list of all subdomains, inner and outer. We know this. That's how we made the domain. But in case you forget, you can always get this information, or if somebody gave you a mesh, you can query the mesh for this type of information. Okay, those of you who like regular expressions are going to like this. You can play all sorts of games with regular expressions using the names. So you see here, the first one is you're creating a mask. A mask is a bit array of which extracts out materials inner. You can do fancy things. You can extract all material. This is saying extract all materials using a regular expression, or you could say extract things in the top boundary and the left boundary. The vertical bar is OR in regular expressions, and it's useful because you can now do things like this. You take the inner material and outer material, and maybe if you have like 10 different materials and you want to do operations on different materials, and you can go crazy with this masking. You can take the complement using this little tilde. If you overlook that, the tilde is the complement of this, like taking the complement of a set. You can take the complement of a region. You can subtract regions. Here's one region. The total inner and outer, subtract the outer region, and then you can ask for the mask to verify that it did the right thing. And more interestingly, for finite element computations, you can set piecewise constant coefficient functions. So a material CF allows you to prescribe a domain-wise coefficient function. you say that the coefficient function in the inner domain should have this value and the outer domain should have this value, and then you pass this dictionary into the material CF, and it makes a piecewise constant function with the values you gave, 3.7 inside and the value 1 outside. You can also do the same with boundary regions. For example, here is a dictionary of boundary values. On the bottom boundary, you want the value x, you want the function x. On the right boundary, you want the function 2 minus y, and you want to stitch them up together to a boundary coefficient function, and you put boundary coefficient and you pass the dictionary as an argument to it. Okay, and now we can't plot it like this because, you know, how do you plot a boundary coefficient function? So one way to see if you've done the right thing is to interpolate that function using the set only on the boundary, and then look at the interpolated function, and now you'll see that the interpolated function has the boundary values you set, and it's cut down to 0 as expected when you do set on the boundary. Okay, questions?
What's going on with mask? I'm a little confused at what it's really. Why is it printing those numbers?
Okay. Let's see. So this is, for example, here. This is a bit array, and it's telling us among all the boundary regions which ones are to be selected. So here we said T or L, right? And the number there were 4 interface boundaries in this domain, and T, L, B, R. Right. So it's selecting just T and L, and you know the position or the order of of the boundary segment by looking at the mask.
See, an inner is 1, 0, not outer, which is 0. Okay.
It corresponds to mesh.getBoundaries. So if you print mesh.getBoundaries, you see the list, and this is the indices in the list.
Yeah.
And so this could be used for. This probably wouldn't go into bilinear forms particularly, right?
It's more about when you do region operations and making sure you're prescribing the region operation in the right places. And okay. So here, what Christopher was saying, so in the interface, in the first 4, you don't select the first 4, you don't select B, you select L,
right,
and then you don't select R, and then you select T.
And this feeds into other things. I guess I'm asking what other things it feeds into.
These are convenience facilities. For,
okay.
Like for when we did the boundary coefficient function, where was it? Material. When we did the boundary coefficient functions, we said define it on B and R, and you could do. These are things when you make up coefficient functions, you want to know that you're setting it on the right place.
So you don't ask there.
You can also, for example, where it's very convenient, you can ask some domain for its boundaries, and then cut that with some other boundaries, and then define an integrator only on that part.
Oh, complicated. Okay.
So that you would use the mask and feed it into something else then?
Into the integrator, into the linear form integrator, for example.
And it uses those bit arrays.
I think you can try this. So get extracts inner region. We can use cell.
Yeah. What do you want me to do?
Materials inner.
Inner. Dot
boundaries.
Dot mask. If you type dot mask now, then you see the print.
Yeah. Where would you use that?
And now you say materials inner dot boundaries. Okay, boundary.
Dot boundaries.
Ah, okay. You can get band. Okay.
Just insert the boundaries. Boundaries.
Sorry.
Yeah. Princess.
You want the mask?
Yeah.
It should have.
Ah, okay.
This is boundaries of the inner.
I guess I'm asking because you have the free DOFs, and that's a bit array, and you use that all the time. I'm wondering where, you're saying in an integrator you would need the bit array.
Also, if you want to evaluate, like for example, a function over some interface, you want to integrate it, or you want to compute the average on that. You want.
Yeah. Cool.
Yes.
This is a small bit arrays, relative geometry. The Friedhofs are huge, so it's a million prime instances are allowed bit arrays.
Peter?
If you wanted to make a finite element space on the boundaries, so you have defined our mesh of boundary B or R there,
Yeah.
you can just say H1, well, or not H1, you can H1 and then just define the mesh of boundaries, and it'll produce, it doesn't do two H1s with a discontinuity, it actually connects them together.
I don't know.
Did you see what I mean?
Yes? Okay. You,
That's why I have a surface file? Yes. Yes. Yeah. What you can do.
so you're saying H1 mesh, but defined on
Equals
mesh.
the B or R. That's going to be
It's going to be an H1 finite element space on the union of these two boundaries? Oh,
yes.
okay.
And now create a grid function on it and set the vector to 1 that you see where it is defined.
Can we see something? Yeah.
I'm hopefully sure.
Okay. One, do you need the BND or no?
No. With BND. Either you say you define on, but I would.
Oh.
You can also just set the vector to 1, for example.
Okay. We can do that. Okay, and then draw.
Yeah.
Are you sure I'm not going to crash?
I may withdraw, I'm not sure. No.
Oh, okay.
You have to evaluate it then at the boundary, for example, because it cannot draw volume.
Right, yeah. So
if you make a 3D mesh, then you can easily do it. The mesh is Unicube, generate mesh. Dot generate mesh.
okay.
You have two
Mesh equals
Oh, sorry.
mesh.
Does Unicube also has BR boundaries? Or?
And then you have top, for example.
Okay. Okay, and
then draw G.
sorry?
And then draw this G.
Okay, let's see. Top. Okay, there we go. I guess we're facing top. Yeah. Okay.
and then you can compress. You can compress that. Yes. That's a good place to compress.
Yeah, there's a lot of things to compress here.
Take this of ends off. Now compare 1200.
1200, okay. You want me to compress and compare?
Yeah.
Compress. 144, okay. That's good compression.
Perhaps this is also a good time to discuss why you had the mesh around the object that was generated. Go up.
Oh.
Where? Sorry?
Go up a bit.
Yeah.
Yeah, down. This is down.
Oh.
You have the mesh around the generated mesh.
The one you just
can
ran.
discuss.
Yes.
There's two types of meshes, right?
Discuss
this yet.
Yeah, we haven't. Yeah, so this thing is a netgen mesh, which is interesting. But mostly we work with the ngSolve meshes, and so doing the mesh of a netgen mesh makes a netgen mesh into an ngSolve mesh. And if there are further secrets, please tell us. I don't want to go into the one-based, zero-based, and no.
You can say netgen mesh. It's just meshing, and for finite elements, you need a lot more information that is computed on the fly than just automation.
Yeah. Okay. Yeah. Peter.
With that Unicube one, could you just give it the boundary to H1, or do you have to give it mesh defined on? Like.
Oh, you could have just done. I think you could have.
This is the region. No.
Oh, you can't.
Then it thinks you want to define it on a on a volume.
On a volume.
No,
So if you give a string, it will define
yeah,
it on
that's
volume.
true. Yeah. Okay.
So what was that?
There. No is the answer.
Yes, but it does something different.
Okay, now I think it's a good time for coffee. Question.
I see the onto the subdomain is what's the solution to the white, the red and the blue colors. There's no any transition color like the yellow green color on that.
Yeah.
You go up to 22. Well,
Yeah, discontinuous functions.
oh, that discontinuous function.
No, it's not.
This one. This.
I'm sorry. Yeah, move up the number 22.
Oh. This one.
Shows a graph to the information. What's this one?
Wait, 22? Sorry, 22 or 21? This one? This one? This one, yeah.
Rotate, open controls, object, close the objects, deformation slider. Now you see that it's a discontinuous function.
It's a constant function on the inner subdomain and 0 everywhere else.
What happens on the unit cube when you do that?
We did it on the box before with the deformation.
Yeah.
If you have a vector field.
Okay. It doesn't just make the top go up.
This information is also into the vector.
Yeah. Makes sense.
You can deform it using a vector field, but okay, that's another story. Okay. So let's have a break until 11 for a coffee break, and then we continue. Can I?
Hopefully it'll be
I can start.
conversational, like I'll plan some extra stuff. No, that's the
Okay. Hope you enjoyed the break. We will continue with a few more sections before I hand over to Joachim for some of the advanced materials. So we stopped at 1.5 previously, and we are going into 1.6 now. Okay. So this tutorial is on error estimation and adaptive refinement. The usual adaptive loop that's sacrosanct is solve, estimate, mark, refine, and repeat. Okay, so we are going to see implementations of each of these steps in this tutorial. Here's a geometry that I'm told is from the early days of Netgen, 20-something years ago. Without going into the details of the construction of the geometry, this is supposed to be a chip that is getting heated up for various reasons, and I think I wanted to ask Joachim. He's not here. I think Joachim had once told me that it's a Soviet chip. Okay, so here is a problem to solve with a coefficient lambda in front of the div grad operator or the describe grad form, and this lambda has discontinuities. In this, there's one value here and another value outside, and so forth. And we expect the solution, therefore, to have singularities because of these changing material properties. We make the Lagrange finite element space before we start doing deductivity, and here is the coefficient function. You see that there's a very large value on one of the subdomains. And we make a heat source, a uniform heat source in this region called the chip, the one in the middle. And we want to solve the Laplace problem with this varying material coefficients. Okay, so first we write a routine that updates the finite element, the grid function, and assembles the bilinear form, and just use the conjugate gradient method for solving the system. So we compile all these steps into this one routine so that we can keep calling this routine over and over again. Okay, we solve it once. On this coarse mesh, you see that there is the heat entering through the chip and then dissipating outside. Okay, if we want to capture a nice solution, then we have to refine the mesh in some places, and for that we need an estimator or an error estimator. And the estimator that's implemented here is a famous gradient recovery type error estimator, goes by the name of Sienkiewicz-Zhu. And we do the implementation uses an HDiv finite element space and a grid function from the HDiv finite element space. HDiv finite element space is a vector value finite element space with normal continuity. When we take the Lagrange finite element space and we take the gradient of the Lagrange finite element solution, we get a discontinuous vector field. We've seen that in one of the previous tutorials, and we're multiplying by the material coefficient. We get an approximation to the flux. That's a discontinuous approximation. We then set it into the HDiv space to make it normal, to have it to get a function which is a flux approximation with normal continuity. And then, so that's this function. This is what we just made, IH of lambda grad UH. And we look at the difference between this interpolant, this HDiv interpolant, and the flux that is computed from the Lagrange finite element. That difference is a measure of error. When that measure of error is large in some areas of the domain, we have to refine those areas more. So that's how we create an error estimator. So implementation of this eta you can recognize the components here. This is flux minus the interpolant. This is the flux, and this is the interpolant in the H-tip space. Take the difference of it, square, and multiply by 1 over lambda. If you plot the error representation, you see that here is a region where you would need to refine in order to capture the error better. Okay, so this integrate function we've seen before in the tutorial before, but without this argument. This argument is interesting for error estimation techniques. It says that instead of integrating over the whole mesh and giving you a number, integrate over each element and give me numbers corresponding to the integral value on each element. So it's going to return a list where each value corresponds to the integral over a single element. Okay, and these are the values. So these are the estimates for the error in each element. So one value per element, and it leads us to identify elements which can possibly have large errors. And so we use this estimator for deciding which elements to mark for refinement. Here is the marking procedure. You run a loop over all elements and set a refinement flag if the estimator on that element is greater than a certain value that you prescribe. So here it's a quarter of the maximal error value. You can tweak these numbers to get more aggressive refinement or less aggressive refinement. Okay, and then there's a loop over, there's a Python loop here which can be replaced by vectorized alternative. We'll talk about that later. But let's do the entire adaptivity loop first. So we solved, we estimated the error. Now we just marked the elements with high error, and now we're going to refine those elements and then solve again. So now you see what happened. There's more elements here, and you solve the problem again. And if we keep doing this, it'll put more elements in the places where the error is large. And now let's automate the procedure. Here's a calc error function, which has the components of the steps that we discussed individually. It's all put together inside this one function. And using this calc error, we can run the adaptive loop. We solve, increase the refinement level. It's not a uniform refinement, it's a local refinement. Using this calc error, we've marked the places where we need to refine, and this should do the loop. As you can see, we're printing out some of the adaptive iterates. You see how at the corners where you expected singularities, it's picking up more and more mesh points. And the maximal error is going down. Every 5 iterations a picture is generated. Okay, now by 51,000 degrees of freedom, we have essentially converged to machine precision in terms of the error estimator, at least. Okay, and we can plot, I think we've saved the errors in each iteration, and we can plot it to see how the progression of errors as the mesh is locally refined automatically. So you see the errors decrease, and at the bottom are the number of degrees of freedom. Okay, questions? Peter.
This is trying to get normal continuity into the otherwise discontinuous gradient.
Yeah, it's an estimator that says if you make up an improved flux approximation, then look at the difference between the improved flux approximation and the original flux approximation. That should give a measure of error.
Okay, so it's just saying that's the error, and so we're trying. Ultimately, that is. I'm seeing this as I deform it. It's like, except for right at the, the hard.
Yeah.
Edges, it has essentially now almost like H2.
You mean at these points?
Yeah, not there, but like everywhere else, it's like almost has a smooth radial derivative, or smooth normal derivative.
Yeah, it's improving the solution, yeah.
So this is sort of like cheating to get into N2 almost, or H2.
No,
No.
We're still using Lagrange finite elements.
Oh yeah, yeah.
So.
And I also was noting
the solution is likely not in H2 because of nasty singularity there.
I guess I meant not at the boundaries though.
Ah, yeah, okay.
So when you mesh and refine, so what's kind of strategy? It's a kind of splitting elements or any other
yeah. You want to? How is the mesh split? Bisection procedure? You want to say something about the bisection procedure? No.
Mesh splitting.
Bisection. The splitting the element or chain.
It's how's a subdivision? It's bisection.
So and once an element is marked for refinement, it's bisected, and at the edge that gives you improved quality or the best quality possible, and then surrounding elements are refined in order to make it a conforming mesh. Just enough. You kind of see some of the bisections, like this was an original element, I think, and then this element got bisected like that. Other questions?
When you do the timing, so this Python marking loop was the slowest part of the whole loop before vectorization, before switching this marking to NumPy.
I see.
And it's a decision in Python was so slow.
Okay, yeah, I sort of ran over that. Here is the vectorized alternative of how you do without a Python loop. You could do. Okay, so
I just order one Python operation, and the decision is done from NumPy, and the output from NumPy is directly put into the netcat mesh.
This when I went over it earlier, this was a list. Now this list is a NumPy array, and this operation therefore is vectorized.
Yeah. Why is it happening with the refine?
So the elements 2D NumPy, this is also data for the 2D elements. So vertices, material properties, and one. So it's an array of structures. We say refine, we access the refinement bit of all elements at once. It's a NumPy array view of the.
That's a NumPy bit array.
Here, where I think Joachim is explaining what happens when you do this is changing this thing element by element. Each element 2D gets a refine equals true. This is
an array of 2D elements. NumPy is a number array of, how do you call them, user-defined structures.
Yeah.
So basically you can also export the C++ structs to be able to be used in NumPy, so you need to give all the offsets of data and so on. And then you can access them like that. So you can, for all elements in the NumPy array, you can access, I don't know, the element number or the element refinement flag or whatever.
Here's the data type. Yeah. It's a NumPy array of this particular made-up data type.
Quite recent feature in
Okay, if there are no questions, we'll proceed to the next one. Okay, Unit 1.7 is on complex valued problems, particularly complex valued time harmonic waves. Finite element spaces can be built over the real field or over the complex field in ngSolve. I don't know if it can be built over some other things. Can you build it over quaternions? Or okay. No. Okay. Just checking if there's some secret features that are. So here's an example of a Helmholtz equation with a wave number omega. together with impedance outgoing boundary condition. We need complex arithmetic for this. The I, the imaginary unit in Python is 1J. Don't go wild with that. It's just I think electrical engineers like 1J. Here's a geometry made in OCC using a circle and a thin scatterer inside the circle. And let's draw it, and then you'll see, instead of me trying to explain the code. Here's a scatterer, and here's air surrounding the scatterer. Okay. Once you make the mesh, provide it into H1 and give this flag complex equals true, and then you get a complex valued finite element space. And the rest of it is similar to what we've been seeing. U and V are the test and trial functions, and then you can make bilinear forms and so forth. Here in this problem, the source is coming in the form of a pulse, kind of located inside the domain. So we're putting the pulse over here, and it's a time harmonic problem. So the pulse is going to create waves that's going to hit the scatterer and then get scattered. Okay, we do the finite element integration by parts, and formulation of the weak formulation, incorporating the boundary condition. The boundary condition, which was over here, in case you forgot. This is an impedance or outgoing boundary condition, first order outgoing boundary condition, and so the du/dn that came out of the integration by parts gives you this I omega u term. That's the weak form, and that weak form is implemented right here. When you have a lot of terms in the bilinear form, this plus equals syntax is useful. This has been instead of the one-liners, and we put the pulse in here for the linear form, and we now have both the left-hand side and the right-hand side of the matrix system that we need to solve. Here's how we solve the matrix system using the inverse. There are no free doubts in this problem. I'm sorry, everything is free doubt in this problem, so we don't have to provide that flag. And we're drawing the solution as soon as we invert this, as soon as we perform this inversion and solve the problem. And there's a new flag. I think it's new a week or so or less. 2 days. Since 2 days ago, there is this option.
From today.
Oh, from today. Okay. Right. Okay. So this essentially allows you to take this stationary solution, multiply it with e to the I omega t, and produce a time harmonic solution, which you can then visualize as a video. Okay, let's see. Okay, now you can sort of see the scattering happening, hitting the scatterer.
If you open the complex, yeah. This is animate. If you don't have that, you can switch on and off the animate.
Yeah, right. This button is automatically checked because of that option that we provide.
Doesn't matter what the form.
Oh, you want, okay. Okay, you can go crazy with deformation. Where is deformation? Here. Yeah. How about that?
Rotate, yeah.
Okay.
So what does the animation mean? It's
just multiplication by e to the I something t. Yeah. Dude. Sorry. And then taking the real part. Sorry. Yeah, that's important. Yeah.
Okay, so it automatically does what you want for your electric, basically.
Yeah, for time harmonic problems. Yeah.
That's really useful.
Yeah.
Okay.
How do I get out of the? Okay, here. Yeah, there we are. Okay, so I think we already saw this. We explored the web GUI. I should tell you where is the real and imaginary part. It's over here. In this eval, you see the real imaginary part and the norm. And norm is the absolute value, so you can view the absolute value if you want. But then the animation doesn't make any sense because the absolute value doesn't change. Okay, Any questions?
On the draw function, is there a good place to find all the possible flags? Because I figured out later you could do vectors equal grid and all this, and it was very useful.
You might be the 1000th person who are asking this question.
Sorry.
Okay, but it's very recent, very quick, and is subject to change, and so it's not 100% nailed down what the final parameter will be. There will be a list,
Okay.
That's the point.
So the developer is in a state of mind where doesn't want to commit to to the quantum state.
Quantum was started about 2 years ago, and now it was undergoing a major internal redesign, and I don't know, the last 2 months.
And I guess there's plans for WebGL2, and more things might change, or
GPU if it comes.
GPU.
GPU.
Okay, here is a subsection continuing the discussion on waves, especially waves that propagate in an unbounded region. We cannot compute in unbounded region, so we need to truncate the domain. And in order to truncate the domain without creating artificial reflections, the perfectly matched layer is a great technique for doing that. So in this tutorial, we're going to see perfectly matched layer used for source problems and for eigenvalue problems or resonances. So for source problem, the equation is very much the same as what we saw in the previous tutorial. Only the boundary condition has changed. The boundary condition is now an outgoing radiation condition at infinity because the domain is infinite. Okay, so what PML does is to do a transformation that allows you to impose, instead of imposing this non boundary condition at infinity, it allows us to impose a boundary condition in a finite domain. Okay, so we'll see that in a second. First, let's make the geometry. Oh, I forgot to do something. I'm sorry. There. Okay, here's the geometry. It's simpler than before. It's got 2 circles, and it's got a pulse like before. Here's the pulse. Here's a circle of air, and this is an artificial layer where we're going to put this artificial perfectly matched layer in order to make the solution go down and exponentially decay without creating backward waves. Okay, so the PML facility in NGSolve implements this using a technique that from a paper by Colino and Monk, where is that right, Peter? It's a the complex transformation. Yes. That's your thing, right? Oh, okay. Oh, from the previous papers. Okay. So the implementation in NGSolve is there's an object called PML, and you can set a radial PML by providing a strength to the PML, which is sort of the strength of the exponential decay, and a radius of the where the PML region ought to start with respect to this origin. Okay, once you set this, the mesh gets a complex transformation. So if you want the mesh to behave like an ordinary mesh without the PML, you might not get the expected results. Once you set the PML, the mesh has this transformation built in. I'm sorry. And we make the finite element space, and we solve the problem. Here's the Helmholtz problem. You can read off from the bilinear form with this outgoing boundary condition imposed at the end of the PML. The only change is this one line. So you don't see anything. The form hasn't changed. When you look at it, you make the form as if you're solving a problem on this finite domain, but you get a solution like this, which gives you the correct solution on the inside and on this artificial PML layer, the solution decays exponentially. Okay, so this makes it very convenient to jump into to add a PML without thinking about the complex transformation required to program the PML. Okay, now we can do the same thing for an eigenvalue problem. Yeah, Peter.
What's a good rule for choosing the alpha? I'm sorry, I know it's spot.
Okay, for resonance problems, very complicated. For source problems, I think maybe you could look at the distance to, what's the strength of the wave at the entry to the PML, and then kind of estimate. I don't know. Maybe you want to say something, Joachim?
Frequency dependent quadratic eigenvalue problem, as people are doing. I think it's too much now for going into.
No, I okay.
It's a very well, you have more answers than your question was.
Okay, it's a constant struggle. Is my answer.
Yeah, if you're trying to find eigenvalues, you can do a bunch of different alphas, and if you have, say, you know the exact eigenvalue, then you can do plots. I've done various plots of different alphas, and it's like tends to be the case that like after a very small amount of alpha, like you get a good estimate of your eigenvalue, and it's really stable. But then very high is too much. So around 1 or 2 is often perfectly good.
Trial and error, yeah.
But it's ad hoc.
Okay, so we can do the same procedure with setting the PML on this mesh and solve an eigenvalue problem, and that would be a resonance computation. And here is a domain. We argued about the name of this domain. But okay, I didn't want to call it a mushroom, but eventually Joachim won, and we call this a mushroom. But it's not a mushroom. This is air. It's just an opening where the waves enter, and then waves go out, and all of this is air, even though it looks like a mushroom. And outside of this area is going to be the PML. The area of the PML is set. Okay. So we made the domain so that there's a subregion, or there's a subdomain region called PML, and in that region we set the PML just like before, and the remaining steps are very much similar, except I should have noted this. If you want to think of this as an eigenvalue problem, move this omega squared to the other side, and lambda equals omega squared is the eigenvalue that we're going to compute. So it's an eigenvalue of the Laplacian, but it's an eigenvalue of the Laplacian with outgoing strained boundary conditions, so you cannot even expect the eigenvalues to be real. Okay, here is the standard bilinear form of the Laplacian. Here is the standard bilinear form for the mass matrix. What is hidden here is that the mesh already has this complex transformation in the PML. So when I say, yeah, it's a standard Laplacian, well, it's got the Laplacian with the PML in it. Okay. Knowing that, we solve it using an Arnoldi solver for eigenvalues, and it gives you a list of some 50 eigenvalues, I think. And here is a picture of the first one. You see something that looks like a mode that starts off over here and then kind of dissipates in. And this is only one of the 50 modes computed. So if you want to, yeah, okay, I can do that. But let me
open complex subfolder.
Okay, and okay, animation, and here is how you get the other components. So this is a grid function with multi-dimensional grid function. So this is one of the modes that was computed by the Arnoldi, and if you want to get the other one, you increase this multi-dimensional component by, these are all the different modes that was computed by that Arnoldi solver. And corresponding to each of these modes, there is an eigenvalue or a Ritz value. Let me get out. And you can print all of them right here. And you can see that they are complex, and some of them are interest. Some of them have small imaginary parts, and those are the ones with more confinement, etc., etc. And maybe instead of staring at the numbers, it's nicer to view these things in the complex plane. Here are the eigenvalues, or the omega values, the resonance values that were computed by the Arnoldi solver in the complex plane. Some of them are very close to the real axis, while the others are all below the real axis. Okay, questions? Okay, so let's go into 1.8, which is on exploring the mesh topology. This is a sort of a preparatory section for other things which use facilities here, and it helps you answer questions like how do I loop over mesh entities, what edges are connected to a vertex, or what about if I want to connect a list of edges connected to an element, or points of an element, elements adjacent to a face, all of this type of questions. You can answer them using the facilities in this tutorial. So we've graduated to the unit cube. Okay, so that's a three-dimensional domain. Okay, it is indeed the unit cube. Okay, here's how you iterate over vertices. Now, this V, which is an element in mesh.vertices, is an object, and when you ask that object to be printed, it just prints out this thing, V0, V1, V2, etc. And then if you then ask for the data attribute of V named point, then you get the coordinates of the point that represents the vertex. But V itself is something of this type, a type mesh node. It's a simple data structure which knows the number of that node, and we'll come back to that in a second. But let me, before I forget, talk about iterating over elements using this type of syntax: mesh.elements. And then you can provide either volume or boundary, and it'll pick up either boundary elements or volume elements and iterate over it. And you see the type of EL in this iterator. This is getting printed right here. It's an object of type NGS element, and the vertices of an element are being printed here. And the edges of an element, the edges of an element are being printed here. So here the element is a tetrahedron, so you can see 6 edges and 4 vertices per element. Okay, so these objects that we just saw inside these iterators, the node ID objects and the mesh node objects, a little bit more about them. A node ID can be created by passing into it any one of these types, and then a number representing its number in the mesh. It could be a vertex, edge, face, cell, element, or facet. While there are no cells in a two-dimensional domain. And if you want to get the this sort of mesh information, this is the syntax to use for associating you have a node number 20 somewhere in a mesh, but just knowing that number doesn't tell you much more about that vertex. So you have to associate that 20 inside a node ID and then associate it with a mesh, and then you can query points like the coordinates of the point and things like that. Without the mesh information, the node object is just a number. Okay, so the type of V, the argument to this mesh, this is something of type node ID, whereas the result after you apply the mesh to it, you get something called a mesh node. So these are the two objects. Mesh node has mesh-based information, and node ID just has a number. Okay, now if you ask mesh V to return all the edges connected to that vertex, well, it gives you all the edges by asking for edges. And similarly, you can now do a cell, create a node ID. So this corresponds to cell number 1 in a mesh, and you make the mesh node object, and then you can ask what are the faces of this particular element, and similar things. We're in a 3D mesh, so you have faces, and so you can make a face object associated to a mesh, and then ask its edges and elements, and so on. Okay, and we saw that we could pass in volume or boundary to these element ID objects, and that's also useful in order to query for topology information. For example, the type of the mesh. So again, once you associate an element ID with a mesh, you've gotten yourself an NGS element object, which knows information about the global numbers of the vertices associated to it, and so on. Okay, so there's more. You can come back to this page and look at all the facilities, because when you're iterating over mesh entities, sometimes you say, okay, how do I do this? And I go back to this tutorial and say, okay, this is because I don't remember this. So this information is there, and when it's put in the tutorial, then it's a promise by the developers that it will not change anytime soon.
Maybe you asked what is the difference of the cell and the element.
Yeah.
Maybe it's for the volume, it's not a big difference, but an element, it can be a boundary element, so it enumerates the surface elements.
Yeah.
But there's a different idea to the faces, where the faces are all faces in the mesh.
Good point. Okay, one more thing before we quit this discussion about enumerating quantities of the mesh, which is degrees of freedom. This requires more than a mesh, because this degrees of freedom corresponds to a finite element space. So if we have a mesh and we have a finite element space, then we can iterate over degrees of freedom. For example, here is a Lagrange finite element space on this mesh, and you're looping over all edges in the mesh edges, and you're asking the finite element space, what are the degrees of freedom associated to an edge? So this is a finite element space of order 4. A degree 4 polynomial on an edge is determined completely on that edge by 5 points. So if I remove on that edge, if I remove the 2 vertices, the edge degrees of freedom, that we should see 3 degrees of freedom, and you're seeing 3 degrees of freedom. And the numbers of those degrees of freedom for every edge. You could do the same thing. What are the degrees of freedom associated to an element instead of an edge? So here is loop over elements over all volume elements, and then we're asking what are the degrees of freedom associated to that element, and the outcome's a list of many degrees of freedom because it's a degree 4 element. Okay, any questions? There's also the help feature, which is useful. You can, instead of asking me questions, you can ask help questions. No questions. Okay. Okay, we've exhausted Unit 1, and we will go into Unit 2. Joachim?
Yeah. You continue.
I continue. Okay. So maybe around noon or something, I give it back to you, or try to. Okay. 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 So this Unit 2, Chapter 2 is on advanced techniques, which Joachim will cover. So this 2.1 is kind of intermediate between beginner and advanced, maybe, and it talks about some mathematical techniques for preconditioning. It could be useful if you want to solve your problems faster using your own preconditioners. Knowing how the usual preconditions are built into ngSolve allows you to extend it to problems that you want to solve. So here are some built-in preconditions. If you want to, the 2.1.1 is on standard preconditioning facilities given inside ngSolve, and then the next one we'll see how to tweak the standard facilities, and at various levels of sophistication. So the built-in preconditioners include the Jacobi preconditioner, which is in ngSolve is called the local preconditioner, or a block Jacobi, which we'll see, I think, in more detail in the next tutorial. There are direct solvers, which of course you can use as preconditioners, but that's usually overkill, or it doesn't work if the problem size is too big. There are geometric multigrid smoothers, which are very interesting. Using a keyboard multigrid, you can access them, or algebraic multigrid preconditioners using the keyword H1AMG, and BDDC preconditioners that you can access using BDDC keyword.
Shane will go into geometric multigrid preconditions tomorrow.
For fancier spaces, I think, right? Yeah. So this is only on the Lagrange space. I'm not stealing your thunder. Okay, so here's a simple test problem where we solve the Poisson equation, and it's put inside a method so that we can keep using it for various mesh sizes, polynomial degrees, number of refinement levels. You start with a coarse grid and refine a certain number of levels, and with static condensation on or off, and whatever preconditioner you like. Okay, inside the solve routine, you see the same type of statements you've seen before. We make a mesh, we make a Lagrange finite element space, and we make the bilinear form and the linear form. And what is new here is this. A preconditioner object is created before the form is assembled. And then that preconditioner object is being used inside the solver here. So the solver is provided with both the original linear system matrix A and the preconditioner. And inside the preconditioner goes the flag that tells it whether you want to use local, multigrid, or whatever preconditioner. The rest of this is pretty self-explanatory. If you want to solve in level at a certain refinement level, then you take the mesh and refine it as many times as you want, and then solve it, etc., etc. And if you want to condense, then you do the static condensation steps. Otherwise, not. Okay. So let's start with the local preconditioner. We take this problem and solve it using a point Jacobi. Local preconditioner is just taking the diagonal of the matrix, invert the diagonal of the matrix, and use that as a preconditioner. Okay, it's not a great preconditioner, but it does do something. I'm sorry, I didn't execute this. And I forgot to point out that this routine returns two numbers. The numbers it returns are number of degrees of freedom and the number of iterations done by the conjugate gradient, preconditional conjugate gradient. So here, going back here, the number of degrees of freedom is ridiculously small, 8, and the number of iterations is also small. If you go up to 9 levels of refinement, then you are solving larger problems, as you can see, from number of degrees of freedom to 8 to 197,000 degrees of freedom, and these are the number of iterations. The conjugate gradient the number of conjugate gradient iterations goes up considerably. So not only is each step more expensive, but you must also do more steps. This is the double whammy problem of not having a good preconditioner. Okay, if you use a different, more powerful preconditioner, multi-grid preconditioner, instead of the point Jacobi or the local preconditioner, you just need to change the keyword preconditioner argument keyword argument from local to multi-grid, and you see the number of iterations are pretty much constant. The problem size has gone up, and each step is more expensive, but the number of steps is constant. Okay, and here's the difference in pictures. Oh, it's not really fitting, but the local is the point Jacobi. The number of iterations plotted here is going up, whereas for multigrid, the number of iterations flattens out. Okay, in ngSolve, the multigrid for higher order spaces, it uses the lowest order multigrid and then some smoothing techniques. So to explain this, here's a high order space where H and P are varying, and here is the subspace, the finite element subspace with the lowest degree, P equals 1, and then you have these subspaces with edges, faces, cells, and so on. And you can decompose the matrix, the matrix which you want to invert and solve the problem in this block partitioning using the vertices, edges, faces, and cells. So the multigrid implementation for a high order method uses an H version multigrid for the lowest order block. The H version multigrid is just multigrid on the P equals 1 block. And then we do these local block smoothing for high order bubbles and functions. Okay, so we again call this problem this function, but now what we are changing is the polynomial degree. We're changing the polynomial degree from 1 to 10, and you see how the degrees of freedom are increasing and the iteration numbers are also increasing, perhaps somewhat mildly, but it is increasing with degree P. If you do static condensation, now you turn on this flag, then this gets a little bit better. You see, instead of these numbers that the 20, 29, 30, and so on, you see better numbers here, and they seem to have stabilized. Okay, now another general purpose preconditioner in ngSolve is the BDDC preconditioner. There's a whole other tutorial on it, but let's just see how to use it without knowing what's inside. We just put this flag preconditioner equals BDDC, and then we do the same experiment we did before with varying polynomial degrees, and you see the number of iterations are more, but this preconditioner, each iteration of this preconditioner costs less than the previous one. So this is each step is cheaper, but you have to do more steps. So and this element-wise BDDC preconditioner is very good for both shared memory parallel architectures and distributed memory architectures. So there's more about this in this tutorial, and depending on time we'll decide whether we go into that or not. Questions? Yes.
Can you, so when you turn on the condensed flag, it means that you are creating the condensed system, so you do static condensation and then you use the preconditioner there. Can you use as a preconditioner the preconditioner that has been built for the condensed version of the system when you are solving the non-condensed
system. Similar to what, I don't know, Uberek is doing, for example.
So you want to solve the non-condensed system,
using
and you have doing this block factorization as we have seen before. Condense out the internal data freedom, then we can reduce it to solve the sure complement matrix.
Yes.
Okay. And we iterate only on the sure complement matrix. When we are doing 10 iterations, we have to apply only the sure complement matrix. And after the iterative solvers, we can recover the internal variables.
But you are constructing your preconditioner on the condensed system.
Correct.
But can you construct a preconditioner on the condensed system and then use that preconditioner on the non-condensed system, on a non-condensed solver?
No.
No,
but it doesn't make sense to me to do this.
Yeah. But you could, as we learn in the next, sorry, right?
Yeah. It doesn't make sense. So you condense, solve the smaller system, and then the precondition solves the smaller system. So in every iteration, you're touching only the coupling disappear. We do not want to recover the internal variable in every iteration to save operations.
The condense part is of the exact local stuff.
But it should be more pure robust in theory. Whereas it is more pure robust. So
the condensed system depends less on P than the uncondensed system.
Yeah. But even if the precondition with the conditioner built for the condensed system, the non-condensed system will be.
That makes sense. Okay, you go from the condensed system to the full system by using this harmonic extension into the elements. And this harmonic extension can be done after the whole iteration. We do the transpose before the iteration, we iterate on the condensed system, and then recover the internal variables. And so we have a solver. Now I know what you mean. We have a solver for the original matrix. Okay, if you want, you can also make a preconditioner for the original matrix.
Yes.
By recovering the internal degree of freedom in every iteration of your Krylov space solver. But if you do so you do unnecessary computations, you can do the same result by doing the reduction before and after the iteration, and you do not have to do it in every iteration step. You could do it in every iteration step, but then you do just not work.
You're free to do more work.
No, you have to plan it.
So, for example, you show that sometimes if you do this type of precondition, you get more pure robust than without doing the condensed. Probably because if you do static concentration, as you just saw on the full system, this is generally more pure robust.
Yeah, if you do the preconditioner for the precondition for the condensed system, for the original system, depend less on E than if you do the preconditioner for the full system. Yeah. But then we do the precondition for the condensed system, for the condensed matrix, we get the same iteration count, but with less stress. But now I'm mistake. If you do, for example, an eigenvalue iteration, an eigenvalue solver, or you use a preconditioner for a Rayleigh quotient minimization, then you have to recover the internal variables in every iteration. Yes. Yeah. Then you
use themes, for example. Use themes or not design.
For a linear system, it does not make sense. But for example, for an eigenvalue system, it does make sense.
Okay, looks like I'm not handing over back to you at 12, right? I continue with these?
You continue, yeah.
Okay.
Lunch, yeah.
Okay. All right, so 2.1.2. This section is on construction of preconditioners, especially if you know that certain problems require a certain type of smoother, and you have to construct a smoother. For example, one of the famous developments was for H-code type spaces, you needed certain kind of block smoothers, and that worked. And maybe tomorrow you come up with another problem where you need a different type of block smoothers. What do? You can make your own blocks, and how you do that is explained in this tutorial. And you make your own blocks. You can do smoothers like Jacobi and Gauss-Seidel using the blocks you select, and then you can combine them to create a preconditioner. Okay, so we're going to import everything from ngSolve, and in particular, this facility gives you the estimates from a line source iteration of minimum and maximum eigenvalues of the precondition system. Okay, so here's a setup which is common to all the problems, all the test problems we're going to run through this tutorial. It's back to the unit square, and we got a problem, simple problem that looks like this with the lower order term included in the Poisson equation, and this sets up the mesh, finite element space, and so forth. And here's the assembly routine. And now, once we have the metrics, let's talk about constructing a Jacobi preconditioner. Okay, again, splitting the matrix into 3 degrees of freedom and the remainder, like we did for the Dirichlet in the discussion of the Dirichlet boundary condition, we can write down the point Jacobi preconditioner, ignoring the constrained degrees of freedom, as this matrix. It's a diagonal on the 3 degrees of freedom, a diagonal matrix, and take the inverse of the diagonal matrix. So you have this. You have a diagonal matrix here and padded with enough zeros to make the matrix of the same size as A. This is made automatically using the create smoother function in ngSolve. Okay, the point Jacobi is given by this create smoother, and the name comes from the fact that the Jacobi iteration is a smoothing iteration. Okay, now how do I check the effectiveness of this as a preconditioner for this operator? Because it's very easy to compute. It's just inverse of diagonal entries. You pass it through this eigenvalue underscore preconditioner and ask it for estimates on the spectrum, maximum and minimum eigenvalues. It gives you these estimates, and if you look at the ratio of the maximum eigenvalue to the minimum eigenvalue, you have an estimate of the condition number. You see the condition number is 188. Okay, now this is a number. We don't have a point of reference for this. If we want to know if this is any better, well, better than not doing anything, or in other words, what if we don't precondition at all? That's like preconditioning by the identity matrix. So we repeat the same steps with, instead of point Jacobi, we plug in the identity, and then we see if we gain anything by doing this point Jacobi. There are a couple of ways to make the identity matrix. One is projection into the 3 degrees of freedom, or just identity matrix, which is super easy. And we send that in as a preconditioner, the identity preconditioner, and ask for the same condition number estimate, and you see it's about twice higher. So we did gain something by doing the point Jacobi. It has reduced the condition number. And the manifestation of that in a solver, if you send it to a conjugate gradient, you will see the manifestation in the number of degrees of reduction in number of degrees of freedom. Here's the point Jacobi precondition conjugate gradient, and the solution. I think this is the same solution we saw before, same problem. Okay, we can do the same a point Gauss-Seidel smoother. We can do the point Gauss-Seidel smoother using the same object called this Jacobi smoother as follows. It's a different iteration, but made possible by the same object. The idea is to use this method. So this is the point Jacobi we made earlier. That object has a method called smooth, and if you run that iteration, it's actually doing the Jacobi, the Gauss-Seidel iteration, not the Jacobi iteration. And it also has a smooth back option, which is doing the Gauss-Seidel in the reverse order, and we'll see that also. Okay, here's how you program such an iteration. You want to call this smoothing iteration a couple of times, and then and eventually it converges to the solution. Here we're doing something like 500 iterations. Okay. Okay, I guess in 500 iterations, the residual has gone down 10 to the minus 8, but not really close to the machine precision. But it seems like visually you've gotten the solution. Okay, we can combine a forward Gauss-Seidel and a backward Gauss-Seidel, and now might be a good time to introduce preconditioners as Python classes. So if you want one preconditioner to do both one Gauss-Seidel sweep and a backward Gauss-Seidel sweep, then you have to incorporate both of them into the preconditioner action. So a preconditioner is always inherited from this object, from the base matrix object. You can call it by whatever name you want. Here we're going to do backward and forward Gauss-Seidel, so we're going to call it symmetric Gauss-Seidel. And here is a small Python class inherited from base matrix. This is the constructor. It's essentially calling the base class constructor, and then it's setting a smoother. This is going to be the point Jacobi object, which knows how to do these methods. Whatever is this object, it needs to know to smooth and to smooth back. And the smooth and the smooth back is part of multiplication method of this preconditioner, which means this multiplication method is doing y equals preconditioner multiplied by x. So if you want to create another preconditioner, the critical routine you have to implement is the action of the preconditioner on a given vector. If somebody gives you a vector x, then you have to do preconditioner multiplied by x and return that in y. And here we're doing this Gauss-Seidel forward and Gauss-Seidel backward, and then returning the y. That's the multiplication operator for this preconditioner. And once we do that, then we can just create an object of this class and then pass this object into a solver like conjugate gradients. And you see that instead of the 500 iterations and the residual not going to 0 yet, once you do the Gauss-Seidel backward and forward, in 33 iterations you have the solution. And you can confirm that the condition number also has reduced considerably from whatever it was 1600 or something before. Now with this preconditioner you have 20. Okay, you can improve the situation further if you're willing to pay more. Paying more is making the cost of the smoothers more. You could do more smoothing iterations, or you can make smoothers with bigger blocks instead of just one diagonal inverse. So here is an example that constructs vertex-based blocks. So a point Jacobi is taking a diagonal corresponding to a vertex value and taking its reciprocal. Now instead we're taking all the degrees of freedom connected to one vertex all the degrees of freedom in the collection of elements touching a vertex. That's a vertex patch. So we're going to invert the system restricted to that vertex block. So instead of doing one diagonal inverse, we have this block inverse on this vertex patch. But to do that, we have to identify vertex patches, and this you can do by the mesh topology routines we querying mesh objects routines in the previous tutorial. So that's what's going on here. We run a loop over all mesh vertices, and then we have to extract the degrees of freedom connected to the elements of that one vertex. So here is a loop over mesh vertices, and for each vertex V, we take an element in all the elements connected to that vertex. And then we extract from that element the number of degrees of freedom associated with that element, make a set, take its union with whatever the degrees of freedom are. So you have a union of the degrees of freedom of all the elements connected to a vertex. This is set union operation. It's like plus equals, but for sets. Okay, and that gives you, it's a Python loop, so yeah, it's slow, but it's good for experimentation. And you get a list of blocks, and they look like this. well, it's not pretty to look at, but okay, sets of numbers, lots of numbers. But you can take this information and then you can pass it to create block smoother. And that what that does, instead of doing 1 over the diagonals, it's going to do inverses over all of these blocks, and you have a list of block inverses. And you can pass this to the eigenvalue preconditioner, and well, you got some condition number. Not that great, but okay. Sorry?
Now you know.
Okay. And we now there are other things you might want to try. You might want to instead of doing this particular block smoother, you may want to do a block Gauss-Seidel back and forth using these blocks instead of the point Gauss-Seidel back and forth, and that's done by the same way. This is the symmetric Gauss-Seidel method that we implemented in one of the previous cells, and you send all the blocks to this symmetric Gauss-Seidel, and you will get a considerably better preconditioner. Condition number 2, 3, something like that. You can improve better. You can improve even more if you provide a coarse grid correction, which is now more expensive. But so as you increase the expense of your preconditioner, you expect to do better. How do we do the coarse grid correction? One way, the way that's explored here, is to collect all the vertex degrees of freedom and then make a bit array pointing to which are the vertex degrees of freedom that should form your coarse system. And using this, just like the Friedhoffs, using the bit array to point out which are the degrees of freedom that should participate in this coarse inverse, you make a coarse inverse, and then the coarse inverse plus the smoother becomes your new preconditioner. So here we're identifying all the vertex staffs into a bit array. The finite element space has more than vertex degrees of freedom, but if we just take the vertex staffs and call all the vertex staff C, then we can sort of decompose this matrix into this coarse degrees of freedom and the remaining involving the fine degrees of freedom. And so what we want for the coarse inverse is this, is the inverse of A restricted to the coarse degrees of freedom. And again, now once you know this technology with the Friedhoffs and the bit arrays, it's super easy to get the inverse restricted to a subset of the matrix. You just provide this bit array vertex staffs, and it has either true or false, and the true corresponds to the vertices over which you want the inversion to take place. So you do this and you get this matrix. Okay. Now this matrix by itself, it's not a good preconditioner. This is just taking the coarse grid inverse. It's not a good preconditioner because it's got a big null space. You can see the zeros here, and you might get confused about this if you make this preconditioner and then you send it to the eigenvalues preconditioner facility, and you find that the condition number is as good as possible. It's heaven. It's 1. You cannot have a lower condition number. But this is because the eigenvalue preconditioner only sees the operator on the range of the preconditioner. So it ignores this null space. So you have a large null space that makes this preconditioner not useful by itself. So you have to combine the coarse preconditioner with a smoother in order to get a good preconditioner. And that is an example of an additive 2-grid preconditioner. And the implementation in ngSolve is super trivial. It's just say the coarse preconditioner that you just made plus the block Gauss-Seidel smoother you just made, you add them up and you get a preconditioner. And that's the 2-grid preconditioner. Okay, and once you do that, you see the eigenvalues coming out, the condition number coming out to be something like 2. The maximum eigenvalue divided by the minimum eigenvalue should be around 2, which is a good preconditioner. Now, instead of this additive combination, one of the things you can do is a multiplicative combination that gives you a multiplicative preconditioner. Okay, but I'm getting ahead of myself. Let me just show you the result of applying the multi-grid preconditioner, just to tell you, how it compares with what we've done so far. Okay, we have made the problem size larger. What is it? 100,000, something like 100,000. Okay. We go into we use the vertex patch blocks routine that creates the blocks corresponding to each vertex, and then we make a smoother out of it, and then we add the multi-grid preconditioner and the block gas idle, the custom block gas idle method that we just did using the vertex blocks we made, and by adding them up, we come up with a multi-grid preconditioner with this block gas idle smoother. And here are the eigenvalues. It is somewhat similarly conditioned as the previous two-grid method, but is much faster. Each preconditional action is much cheaper than before. Okay, questions on this? Yeah. Why MG dot math? Why what? Why the MG dot math? The MG is the multi-grid preconditioner, or from yeah, I know. Yeah. But then the dot math. Dot math is the matrix corresponding to. But they were different types. So MG's. Sorry, you wanted to say something?
The preconditioner itself can act as a matrix, and it's optional to extract also the matrix of the preconditioner. It's what of that?
Is that MG.math like an explicit matrix, or is this just some action of that?
It's a linear operator.
Oh, okay.
Yeah, not a sparse matrix. I mean, it won't be sparse.
The preconditioner was more, it was the half of
the G plus the block.
Really?
I think you need the measure.
Okay, well that would be.
I think you also should work without the measure.
Let me see.
Yeah.
Yeah, seems like. Yeah, that's better. Okay. All right, I continue to the next tutorial. Okay, we get 2 more tutorials to go before lunch, I guess, right? Lunch is at. Sorry?
Just 2 more fits for till lunch. Yeah.
Okay, I will make it fit. Okay. Okay.
Or take the time. Yeah.
Oh no. We should fit. I think you and Christoph you all have to speak. Okay. So this we saw the multi-grid preconditioner, how to use the multi-grid preconditioner previously, but this is about diving a little deeper into the construction of the multi-grid preconditioner itself. The objective being that if you need to change or tweak something in the algorithm, then you can use this tutorial as a starting point for your own purposes. So there are 2 types of multi-grid preconditioners: the additive and the multi-level preconditioner. The additive, both of them require these are geometric multi-grid preconditioners, so they require a hierarchy of sequentially refined meshes and nested finite element spaces. These are the nested finite element spaces. The dimensions are NL for each of the VLs. The critical ingredient for multi-grid to write a multi-grid algorithm is a prolongation operator. The prolongation operator is a implementation of the process of the embedding. The embedding is an identity operator. It's trivial mathematically, but you want to be able to write it in terms of the basis of these spaces. So that becomes a matrix, a computational object, and ngSolve gives you that matrix, and then you can play around with that matrix and combine it and so forth. And it's also worth noting that the operator at the finest level generates all the operators in the coarse level by this formula provided you have a finite element type method or Galerkin type discretization on these nested sequences of spaces. Okay, and we're going to use that in a second. So here is the mathematics behind the construction, and we're going to try to make the Python code look very much like this mathematics. So the two-level preconditioner involves like this point Jacobi that we saw before, a diagonal inverse, the D inverse, plus the inverse at a coarser level, which is presumably less expensive, and then this integrate transfer operator. So you want to solve on a fine grid, and you have a coarse grid, and you're willing to solve on the coarse grid. That's your willingness to solve on the coarse grid, and then you have to bring the solution back to the fine grid. That's this operator. But in order to solve on the coarse grid, you have to bring the data to the coarse grid. That's this transpose operator. This is the restriction operator. This is the prolongation operator. If you have all of these operators and then you add a smoother, you have a two-level preconditioner. But a two-level preconditioner can only go so far. The multi-level idea is just do this recursively. So instead of doing this, replace it with the same idea and go further down. So that's the idea of the multi-level preconditioner. So instead of the exact inverse at the coarser level, you repeat this algorithm and go down to a further level and so on. So this is an additive multi-level preconditioner. And here is an implementation that hopefully looks like this very soon. I'll give you a long form implementation which does not look like this, and then show you two lines that look exactly like that. Okay, first setting up the scenario. A uni-square mesh, usual bilinear form for Poisson, and here is the multi-level preconditioner, the additive multi-level preconditioner in long form. So you make it again, you make a class inherited from the base matrix class, and it is being given a coarse preconditioner, and that coarse preconditioner gets stored, and it creates a smoother using the free degrees of freedom. And here is the multiplication routine. This is where the preconditioner action is programmed. This is the action of the y should contain upon exit the preconditioner multiplied by x. We call this preconditioner CL, and this is the formula we want to implement. And if you look closely, you will see this formula here. The key object is this. ngSolve provides finite element spaces with these prolongation object, and that prolongation object knows how to do the restriction, which is this what we call P transpose in the math above, and it also knows how to do prolongation itself, which is just multiplication by P. So here we are executing the steps in this formula. You have to multiply by P transpose times X, and then apply the coarse inverse, apply the coarse routine with the coarse preconditioner, and apply the inverse of D. So you see all those steps. And there are some methods that are required for this preconditioner, like it should be able to return the shape in order to check dimensions. It should be able to create temporary vectors and so on. Okay, so here is a.
Sorry, what
yeah?
data type is CDOS?
Sorry?
What data type is CDOS? It's just a list of integers, or?
CDOS. Oh, okay. Yeah, it's a int range.
Range.
Yeah, it's well, you know.
Intervals, yeah.
An interval, right? Starting from this number up to number plus 200 or whatever. Okay. So now we're talking about the int range. This is updating this y vector in a certain set of degrees of freedom that's prescribed by the int range, and all this magic happens because refined meshes have degrees of freedom hierarchically set up. Okay, a super exciting 3-line formula here for the same for the same class, which does exactly the same thing. Again, we use this object, we get what we call P, and we get what we need, D inverse, the smoother, and then we just combine it like so. Return the inverse of D plus P multiplied by the coarse preconditioner multiplied by the P transpose. Okay. Okay, let me execute that, and let's see, I executed this, I hope. Okay, now inside this loop, we're going to make this preconditioner for various levels from 0 through 8, and then we're going to compute the condition numbers and see how good it is. Okay, we went from 61 degrees of freedom to 200,000, 787,000, I think. Oh, we're not done. Oh, 3 million degrees of freedom. Okay, it's pretty good. Condition numbers are right here, and it's stabilizing. So we declare that this additive multigrid is working.
So here we're using H1 linear, right?
H1, yeah, just Poisson, yeah, on a nested sequence of.
Maybe the comment that there are only a few spaces that have this prolongation operator.
Yeah, that's why we need to listen to your talk, right? Yes. So I don't know which spaces have the prolongation implemented. H1.
The H-curl space has it.
Okay.
What was the most important for the application?
Right.
And the lowest order HDIF, maybe I'm unsure about this, but Kucheng is showing us for the full linear DG tomorrow. This was not in. Definitely not the higher order spaces.
Yeah.
Since for higher order preconditioning, we usually go back to the lowest order preconditioning. There are not so many, but this algorithm is generic. So whenever the space can do it, this should work.
Okay, and so I'm running out of time. I definitely don't want to encroach on lunch, so I'm going to skip the multiplicative part. But there is a implementation of a standard multiplicative multigrid algorithm.
Yeah.
Sorry.
I think you should do it,
then I won't get to. Do you want this or BDDC?
This.
Ah, you want this? Okay. Okay. So we skip BDDC.
After lunch.
After lunch is you. All right. Okay. So here is a multiplicative algorithm. Okay, this is textbook V-cycle. We first do a pre-smoothing. We're defining this operator. So we're given input D, and we're producing preconditioner action W. So first we do a pre-smoothing using the input vector D, and then you do a coarse grid correction combined multiplicatively with the pre-smoothing, because you have the same output of the pre-smoothing coming up here, and you're taking the residual with respect to the W that came out of the pre-smoothing. And then after that, with the same W that came out of the coarse grid, you're doing a post-smoothing, and that's with some other. This could be Jacobi or some other fancy operator, smoother if you have access to some other smoothing operators. Okay, that's the algorithm. Okay, so we're gonna realize this algorithm in a Python class using the usual setup, H1, unit square, and so on, but the technique is similar for whatever domain. Here's a preconditioner class. Same as before, there is a coarse preconditioner argument that gets stored. So this is where the recursion happens. If you call this multiple times at multiple levels, at level L, you have the data structure for all the levels below stored inside this. And then you have a smoother created right here in the constructor, and here is a critical routine where the preconditioner action happens, the multiplication. So W is supposed to give you the result of the algorithm. Okay, you get the prolongation operator like before. Now it's an operator, and we'll use it in a second. The local preconditioner that was passed in as that was created here in the constructor can do the smoothing operation and the smoothing back operation. So this is the pre-smoothing operation, and this is the post-smoothing operation. Once you do the pre-smoothing operation, excuse me, you compute the residual and apply the transpose of the prolongation, the restriction operator, and then the coarse preconditioner, and the same pattern that we've seen before, and then smooth back. This is the implementation of the multiplicative multigrid cycle. And you use that one cycle as a preconditioner, and then you can look at the resulting condition numbers, and you see the condition numbers are very good. So did we oh, it's still running. Okay, yeah. For even for 3 million, it's 2 point something. So previously, I think for the additive one, it was 20. So it's a factor of 10. Okay, I mean, if these numbers are are too abstract or meaningless, you can just plug.
Also, a conditioner is much better in terms of timing. Pretty close.
Okay, I didn't check that. Yeah. You can put it into a conjugate gradient and see the practical efficiency. So we're solving a 3 million by 3 million problem, and 17 iterations on commercial, not a heavy grade laptop. Okay, projection. This is a variant of the multigrid where imagine you don't have the hierarchy of meshes, and you're given the mesh at the fine level. If you're given the mesh, if you're given the operator at the fine level, then you can create coarse level operators, provided you have prolongation operators. And so here now we're gonna make a mesh, and we're gonna successively refine it, and we take the finest mesh and give only the finest operator, finest A, to the multigrid method, and it is supposed to find out what the coarse operators should be, and it's going to do this formula. It's going to make the coarse matrices, and that is happening in this class. This is the projected multigrid, and here is the making of the coarse matrices. See the restriction that came from the prolongation object, the prolongation itself that came from the prolongation object, and this is P transpose matrix times P. Okay, so here is the projected matrix, and then there's the. We're not doing this multiple levels. We're just doing one estimation on a fine mesh, because we don't have these multiple levels. The matrix is being made from the finest matrix. The condition number is more or less like before, and the performance is also more or less like before, exactly like before. Okay, I think maybe this is a good point to stop for lunch. I think I see that everybody's exhausted. Thank you.
We are in preconditioning section. So the last version is a P version, BDC preconditioner. Okay, a lot of text. So what's the idea is we build a larger matrix A tilde, which is cheaper to invert, which provides us a preconditioner. And this picture here says everything. We are building our finite element space like this. We have high order, 10th order finite elements. We connect them only in the vertices. That's the reason these are the wire basket degree of freedoms. But we make them discontinuous between the elements. We break the continuity along the edge by duplicating the degree of freedom on the edge. The claim is we build a stiffness matrix for this larger space, mainly discontinuous space. The claim is this matrix is cheaper to invert than the original stiffness matrix. And we can do a static condensation now not only of the internal degree of freedom but also for the edge degree of freedom. We do a static condensation locally. The element sure complements are only say from the lowest order finite elements, and then we invert the matrix for the lowest order finite elements. Or do a preconditioner there. And this is a BDDC. The basic idea of this BDDC preconditioner. We are inverting this large matrix E tilde, but after applying it, this matrix, we get a discontinuous function, and we have to make it continuous. And this is this R matrix doing, so arithmetic averaging or weighted averaging. Okay, so this BDDC precondition, I can run a few of these examples. I think, can I make it? We have again a test preconditioner with options, whether we do condensed or non-condensed versions.
This BDDC why does not have a smoother?
Pardon?
The BDDC there's no smoother, they only have a
Okay, so the outcome of the BDDC, of the A tilde is a discontinuous function. But after applying this averaging matrix R, it's a continuous function.
So A tilde is a bigger one.
So A tilde is larger, R is a wide rectangular matrix. And you can analyze it very well. So you have to analyze the norm of the R matrix, which is related to H1 half and H1 half 0, 0 norms. And you see it goes only logarithmically in P. They have a very mildly growing in P. Why we like it, this works very nice also in parallel. You don't need overlap. You can do everything locally on the subdomains, so the local static condensation locally on the subdomain. And so this one is our favorite for distributed memory parallel computations. Okay, question is what are now the coupling dwarfs? There are the vertices obviously in 2D. In 3D, what are the coupling dwarfs? Vertices or edges. Both have pros and contras. Vertices are less, but vertex evaluation is less continuous, it goes with P square in 3D. Vertex evaluation in 3D is much more problematic than in 2D. In 2D we see only logarithmic dependency of the condition number of the polynomial degree, while in 2D logarithmical, while in 3D it's polynomial in P. So edges are fine to make it continuous on edges in 3D, it's fine in terms of condition number, but of course since the coarse grid system is much richer, and a good compromise is have to say first the quadratic bubble continuous on the edge. We have now many built-in options what kind of degrees of freedom we declare wire basket, which to make continuous. Default is 3D, the first edge bubble. Okay, I was not prepared to running it. Okay, there are a couple of tests. What we see, the spectrum is always from 1 to the largest eigenvalue. The analysis says that the smallest eigenvalue is always greater or equal than 1. Okay, and then you have to do something about the lowest order system. Either use a direct solver, or, for example, you can combine it with a multigrid method or an algebraic multigrid method if you have large problems. Okay, I think that's enough to explain the ideas. You can do some experiments later. You can set the wire basket as you wish. There was a question before, are these wire basket dwarfs always vertex values. Not always. The wire basket doves are the ones which keep the continuity in this enriched space. If you think on edge curl elements, then you take the edge, lowest order edge degree of freedom. If you think of some hybrid DG method, then the mean values on faces are the wire basket doves. It depends very much on the function space, which degrees of freedom are considered to be wire basket. Yeah. Too much I wanted to say about that. Okay, so these are the built-in, mainly the built-in options for preconditioners in ngSolve. Tomorrow we will see that there is a much larger class of preconditioner now. Thanks to Umberto, he built the interface to PETSI. Now we can also say preconditioner from PETSI. We take this kind of PETSI preconditioner, so the whole world of PETSI is now available to be used as a preconditioner in parallel or also on sequential computations to be used in some iterative method in ngSolve. Okay. What can you do with a preconditioner? You can solve linear systems, or you can also do eigenvalue problems. Here I'm looking to write our own eigenvalue solver for generalized symmetric positive definite eigenvalue problems, as for structural analysis, for example. We have a stiffness matrix A, we have a mass matrix M, coming from U cut V, in the easiest case, unit square. Build the stiffness matrix from grade U cut V, build the mass matrix from UV. One of the simplest methods is the inverse iteration. You iterate by applying A inverse M, iterate this, and then this one will converge to, if it's single largest eigenvalue, to the eigenvector corresponding to the largest eigenvalue. What we want to do is a pinwidth iteration, so we are minimizing the Rayleigh quotient. So the smallest eigenvalue is the minimizer of the Rayleigh quotient. We have here, this is the Rayleigh quotient, AU, U inner product divided by inner product with the M matrix. Okay, we compute the gradient of this Rayleigh quotient. We compute that it is the residual of the eigenvalue problem. And from the gradient, we apply an approximate inverse to the A matrix, a preconditioner for A, to find the search direction. We go into the search direction W, and then we update the previous iterate with this by some factor times the search direction. And an automatic way of finding the update is minimizing the Rayleigh quotient on the two-dimensional space spanned by the previous iterate and the update direction W. What's the pinwidth? To minimize this, we have to compute small matrices forming inner products between current iterate and preconditioned residuals, compute the small problems, and then minimizing the Rayleigh quotient for the small problem means we are solving a 2x2 eigenvalue problem, which you could do by hand or ask SciPy for doing it. Okay, this is what we want to do now. We iterate, we need a couple of help vectors. We start with we initialize the residual with a random number, but project out non-Dirichlet degrees of freedom. So we have now a random vector on the unconstrained degrees of freedoms. The projector projects into the non-Dirichlet degrees of freedom times the random vector. Okay, this is now this pinwidth iteration. We iterate, for simplicity, just 20 iterations, applying stiffness and mass matrix with the current vector, forming inner products. The Rayleigh quotient is the ratio of this inner product, which gives an approximation to the eigenvalue. The residual of the eigenvalue problem, the preconditioned residual. Here we need a preconditioner, one of these preconditioners we have been discussing before. Now we are forming all these inner products, inner product of A, U, W, and inner product A, W with W, to compute this small 2x2 A matrix, 2x2 M matrix. let it run, and the exact eigenvalues is 2. We have a finite element approximation to the small eigenvalues, so we are close to 2, and we see that this preconditioned inverse iteration is converging pretty fast to the eigenvalue. And the eigenvector is this finite element approximation to the sine x times sine y function. It's also interesting if you want to have the first few smallest eigenvalues, you can do a simultaneous iteration. We declare now a grid function with multi-dim, for example 5, so we have space for storing 5 eigenvectors, going to compute 5 eigenvalues and eigenvectors. We need some more help vectors. We are creating new vectors of the same dimension, complex or real, parallel or sequential as the original vector was. We need some more vectors. Now we initialize all of them randomly. Okay, we do essentially the same, but now computing small matrices, minimizing over 2 times num dimensional spaces, minimizing over this 10-dimensional space, which gives us an approximation for the updated eigenvectors. We keep the smallest 5 and add some more from the residuals and preconditioned residuals. So we do this now we iterate over the 5 vectors, computing 5 residuals, 5 updates, computing the small matrices by projecting this stiffness matrix to this 10-dimensional small dimensional space, and solving then 10 by 10 generalized eigenvalue problem using SciPy. And what we see is that now we get approximation to the first 5 eigenvalues, 2, 1 square plus 1 square, 1 square plus 2 square, 5 is double eigenvalue, 8 is 4, 2 square plus 2 square. And we can look at the different eigenfunctions. We have a multi-dim slider here, so we can select different vectors. This was the second and the third eigenvector, so they live in the same space, so they look somehow funny since it's some linear combination between it's any basis for this 2-dimensional space. The fourth looks already, okay, the auto scale is scaling for the first one, but you can see it. Okay, so this shows an application of preconditioner for solving eigenvalue problems as an example. You've seen it's a simultaneous iteration. You're applying the matrix to a bunch of vectors, and this can be optimized since applying a matrix to 10 vectors simultaneously can be done computationally much faster done as applying 10 times the matrix to 1 vector. Here we have now this concept of multivectors. A multivector is a vector of vectors. We have a multivector of 10 components, so it stores 10 regular vectors. And you can do operations. You can add multivectors. You can multiply multivectors with small matrices, linear combinations of multivectors. You can see, you can interpret such a multivector as a high rectangular matrix, where the height is the finite element space dimension, and the width of the matrix is the number of components of the multivector. You can do pairwise inner products of multivectors. You can use the inner product of multivector X with the multivector Y, which gives us a small matrix where pairwise inner products of every X vector with every Y vector are computed. So we function to orthogonal eigenvectors. For example, for reduced model order reduction problems, you want to keep them orthogonal. You can increase the space of eigenvectors. Okay, if we already have one vector from the grid function, we can create a multi-vector of the same type, of the same size as the vector, 5 vectors, 20 vectors. So the space we are iterating for this simultaneous inverse iteration is now iterated over multi-vectors. And it becomes now very short. Here we compute the residual of the eigenvalue problem what means applying the stiffness matrix to each of the vector of the multi-vector, applying the matrix, the same matrix to 10 vectors, applying the mass matrix to the 10 vectors, and scaling each of this component by this vector lambda. We can form inner products of the multi-vector and A times the multi-vector, which gives us now these 10 by 10 small matrices. We solve the small eigenvalue problem, and we see here we're converging to the 5 smallest eigenvalues, 2, 5, 5, 8, 10. Questions about this?
Any reason use a random number for that vector? Initialize the vector using random number.
Okay, we need some initial guess, and so we should have components in each of the eigenspaces. We should not start with some eigenvectors, and we will not fix the space. So this tutorial shows what you might want to do with a preconditioner, and then Umberto is absolutely right. You want to have a preconditioner for the full system, which you can construct from a preconditioner for the reduced system. It's a very nice application for this suggestion. It shows also that you may want to optimize matrix times multi-vector, applying the matrix to 10 vectors in parallel. So it's about 5 times faster applying a matrix to a multi-vector as applying a matrix to each individual matrix due to cache effects.
Is the matrix times multi-vector optimized, or is the matrix inverse type multi-vector optimized?
We only have linear operators. So matrix inverse is also a linear operator. Matrix inverse means sparse factorization and backward-forward substitution for the sparse factorization. Then if the sparse direct solver, for example, Partition supports doing simultaneously solves, then we can benefit from this with for the multi-vector. I think it's used for the Sparse-Kolesky. Maybe it's not implemented for all matrix types, but if needed, it can be. This optimization can be implemented also for matrices where it's not implemented today. Okay, so this section is meant for people who are doing research on linear algebra, doing some iterative Krylov space methods, and want to get matrices from ngSolve and want to design iterations. The other tutorials are more sought for people who are doing research on preconditioning, doing multigrid or domain decomposition, to deliver components which can be used on a higher level of linear eigenvalue, nonlinear solvers. Okay, now we're switching topics a bit. We are coming now to finite element spaces. We have seen H1, now we're looking to bit more interesting vectorial finite element spaces. Let's say H curl, H diff, vector valued function, where the curl operator supported, the diversion is supported. I assume you have seen these lowest order elements for these spaces. These are the typical lowest order Lagrangian finite elements with values in vertices. These are lowest order Nedelec elements where the degrees of freedom are tangential components along edges, integral over the edge of the tangential component. This here is the lowest order Rabi-Atomar element where the degrees of freedom are the integrals of the normal component over the face. And if you do the G element, these continuous elements, they are just polynomials on the elements without any continuity. You can start with piecewise constant. These are the lowest order elements from the Tiram sequence, H1, H curl, H diff, L2. They fit together. If you have the gradient from here, then you end up in H curl and so on. So it's very nice to look at them together. These are the corresponding finite element subspaces from H1, H curl. So if you want to do a finite element subspace of H curl, finite element method in H curl, we just say if E space equals H curl of this order. Then it's takes elements of this type, the edge values, and NGSolve supports elements for all of the spaces, for the whole zoo of elements, for triangles, quads, hexahedra, tetrahedra, also pyramids of every arbitrary order. You can say fifth order on prisms. You can also curves elements, you can vary the order. It's all supported. Okay, how do we build these spaces? Let's first look on how we construct hierarchical basis functions for H1 spaces. I do an H1 finite element space on a triangular mesh, so I make a mesh. Okay, I set now the grid function coefficient vector to be 1 at vertex 70 and 0 everywhere else. Actually, I didn't say that 1, but it's to 1/2, but it doesn't matter. And you can look at the basis function, it's a head function. For H1, then we have basis function on edges. Let's look at them. Okay, you can extract the degrees of freedoms, for example, associated with the edge, with the 10th edge. On the 10th edge, if you do third order, we have two basis functions, the degrees of freedom, and now we set the coefficient vector to the 39th unit vector, draw this, and you see a quadratic function supported on the edge. And the next one is a cubic function supported on the edge. So we have this hierarchical construction, first vertex basis functions and edge basis functions, and finally we have basis functions on the cell. And you see the cubic bubble on the triangle. So it says one basis function on the triangle. And if you want to have a better visualization, you can do a subdivision on in the shader. You see a well-resolved cubic bubble function. Okay, so coming back to this coupling type, now we understand it better. The coupling type of the vertex basis functions are declared wire basket. The edge basis functions are interface stuffs. There are the two basis functions on the edges, and the internal has the coupling as local coupling type. So this wire basket interface local is information, for example, needed for the BDDC preconditioner. Okay, we build these finite element spaces in relation with the chain. For the H1 space, we have the lowest order vertex basis functions and then basis function on edges, faces, and cells in 3D. For H-curl, curl finite element space, we have this lowest order, the one I've drawn above, just the lowest order on the edges, plus a space on the edge. A space on the edge are the gradients of the H1 basis functions. Basis functions on the face, basis functions on the face are a subset as the gradients of the H1 gradients plus some more. Since in 2D it's just a subspace. And also on the cells, the gradient of the cell basis functions have a gradient of the cell H-curl basis function. So you see these basis functions are related. And actually what we do is we have basis functions for the H-curl which are gradients of H1 basis functions, and so on in the sequence. For this, point to Sabine Zagelmeyer's thesis, which is one of the references on the NGSolve side, where these basis functions are all explained very well. Okay, we can look also on basis functions for H-curl. So I selected the first basis function sitting on this edge here. So it's a vector valued space. So the basis functions themselves are also vector valued. You see the small arrows pointing in the direction, and you see the color of the absolute value of the basis function. And I'm plotting the basis function as a vector and the curl of the basis function, which is a into a scalar. But it's a piecewise constant scalar. And this is a basis function, an element-based, phase-based basis function for H curl. You can see it's completely, the tangential component is 0 on the element, so it's tangentially continuous to the neighboring elements, but it's completely 0. If you do HDIF finite elements, you may know the Ravier-Tomar elements and the Douglas-Marini, BDM elements, which are complete polynomials, and the Ravier-Tomar have some more than the polynomials, some px, if you know it. You can choose HDIF spaces, and where you can choose now between BDM or Ravier-Tomar. You say Ravier-Tomar true, then we get the Ravier-Tomar space, which is order between 2 and 3. We can check this function. This is a function which is more than second order. This is in the special Ravier-Tomar space. If we interpolate this given function into a Ravier-Tomar finite element space, we can compute the interpolation error, and we see this function is exact in the Ravier-Tomar finite element space. Okay, you have seen for H curl finite elements, you can do the curl of the grid function. You can always do the native differential operators corresponding to the space.
Actually, I have a question. Can you go back to where you had set UB.set?
Yeah.
So that does an L2 projection?
Ah, the set. Yeah, this is an element-wise L2 projection and averaging of the degrees of coupling degrees of freedom. Okay, so the element-wise L2 projection preserves this function since it's in the element space, and we don't need to average. The averaging does not change anything.
Okay, but what if you did interpolate? Doesn't that also?
So it's also we can also do interpolate. Why not? Okay, so this does not. And we can say if you want to do interpolation with the degrees of freedom, you can say dual is true, I hope. Yeah. And we should. It's the way how it should work, but something didn't like it, and you see the problem. I think if we okay, it might be that the dual shapes for the Ravier-Tomar have some issue. If we do the PDMs, then the set with the dual basis functions works as expected. And what we see also, we have an interpolation error, since in the PDM space, this function is not included, and we have to do some approximation. Look at the error 4.07. If we do the other one, the L2 projection, it's even more accurate. We have a different error. Both.
What does that mean exactly? The dual? Like, what are you doing there?
If you say dual true, it means we do the canonical interpolation using the Ravier-Tomar degrees of freedom.
Oh, like computing the moments.
Yeah. And the interpolate is also doing this. The interpolate is a newer name for set with dual equals true.
Okay, but when you said dual is false, it's literally doing point-wise evaluation?
If we do dual false, we do element-wise L2 projection.
Oh, okay, good.
And then averaging.
Okay.
Okay, so the grid functions and differential operators know what are the canonical differential operators. If you have a trial function in HDIF or a grid function in HDIF, it knows, okay, I'm happy with the divergence. This is an efficient differential operator for this type of space. Since we are computing the divergence or curl on the reference element, and this can be mapped by covariant polar transformations to the physical element. We can ask the HDiff trial function, what kind of operators do you also support? And it tells us, okay, you can also do the gradient of an HDiff function. But this is not a canonical differential operator. It means it does an element-wise gradient. It's more tricky to compute the gradient. It does it via numerical differentiation on the reference element, and it's more complicated to map it to the physical element. It has to take also second-order derivatives of the mapping into account. It's all done. And you can also, for example, draw the gradient of the HDiff function. It's a bit rough here, but if I go back to the Ravi-Atomar space, it's false. Now I have the exact interpolation of this function, and if I compute the gradient of this function, I get the exact linear function. So this gradient is also consistent. For example, for DG methods, for HDiff conforming hybrid discontinuous Gayorkin method, as Christopher will talk more about, we need the gradient also of this, the element-wise gradient of HDiff finite elements. Okay, let me close it. Okay, typical application, what you want to do with H-curl finite element spaces, you want to solve Maxwell problems. Okay, ask Peter for signing the book. They're computing the flux B and the magnetic field E, which are related by material laws, magnetization, which goes to the right-hand side. We can combine everything into one second-order equation, solving the curl problem for the vector potential with this right-hand side curl of the magnetization. Or in weak form, we are looking for a vector potential in this H-curl function space, H-curl finite element space later on, solving the variational problem in H-curl, this variational problem with this bilinear form and this linear form. Okay, I make a small magnet. Okay, we see a cubical box and we see a small rod. This is our magnet. Here we prescribe a magnetization in the rod. The magnet got a magnet and we have an air domain around. Check the materials, air and magnet. We have an outer boundary and the interfaces. Okay, so we have an H-curl finite element space, third order, trial and test function as we had before. We can set material coefficients. In the magnet we have a high relative permeability. Everywhere else we have it 1. So the bilinear form is, is mu inverse here, where the mu is typically relative permeability times the permeability in vacuum. Define the bilinear form here as 1 over mu times curl u times curl v. Okay, curl is a large null space, so this would lead to a singular matrix. You can do it with a Lagrange multiplier. Easier ways to add a regularization term, add a small regular matrix, add a small L2 term to make the matrix regular. Using a BDDC preconditioner for this problem. BDDC knows all the edges, lowest order edge degrees of freedoms should be my wire basket doves. The linear form is the right hand side, what is magnetization vector times curl test function on the magnet. It integrates only over the magnet subdomain. Assemble stiffness matrix and right hand side. I think this was the first time where the task manager came into game. So task manager is, okay, we are starting up threads. Now on my notebook 4 threads are running over the next instructions, and the assembling matrix and vector generates tasks which are distributed around among the running threads. Solve with the recognition system. And we see now the magnetic flux of this small magnet. Okay, same setup for H-curl problems, H-diff problems as it was for H1 problems before. We're talking about eigenvalue solvers. Let's do a Maxwell eigenvalue problem. Left hand side is.
Will you talk about traces later?
No, not so much. No. Okay. Good point.
Which trace is the tangential component of the trace?
Yeah. Okay. This was we were discussing about this. So, for example, if you want to do an u dot v and rho and term as a boundary, what you can do easily is integrate over boundary u tangential trace times v tangential trace. We were thinking, should we just give the u tau times v tau as a boundary without any further comments? As a design decision was that we should say u dot trace times v dot trace boundary integral. And this trace makes clear that it's a tangential trace for H-curl. Or for H-diff, we say if u is an H-diff trial function, if we say u dot trace, it gives us a vector on the boundary in normal direction. It has the same vector space dimension, it's still a vector, it's independent of the orientation of the normal. And we can only use the well-defined traces for the boundary integrals. And these boundary traces can be evaluated in terms of degrees of freedoms associated with the boundary element. Otherwise it's non-native or would be expensive, which we can also get with some hacks.
And if you say curl of the trace, is that a scalar curl, like a rod?
You get, okay, it's a commutative thing, so it's a surface curl of the trace, or it's the same as the trace of the curl. And the trace of the curl gives you a normal vector. It gives you a scalar, but it gives you a vector in normal direction. Like the H-diff trace gives you a vector in normal direction.
You mean you take the vector and you project it, you multiply it by n times n? Is that what you mean?
Yeah, we don't multiply, it directly comes out as a... Yeah. And this is independent of the orientation of the face. So if you want to have the scalar components, then you have to dot it with a vector, and then it's your responsibility how you orient it, your normal vector. Okay, solving Maxwell eigenvalue problem. Of course, the curl operator has a large null space, so we have many zero eigenvalues, which we are not interested in. We want to have the smallest non-trivial eigenvalue, so we have to find solutions orthogonal to gradient of H1. We want to use the pinwidth iteration to iterate for the smallest eigenvalue on the complementary space. And for this we use a projector, a harmonic projection, projecting to the L2 orthogonal subspace of gradients. Get this by solving a Poisson problem, taking gradients, where the input to the Poisson problem is the divergence of the vector in weak sense. Okay, how to get this? So we are looking at the Fichera cube. We have a domain like this. You immediately guess that you will expect singularities at these non-convex edges here. I marked these edges here for geometric refinement here. What it means? It means that we do very strong geometric refinement towards the edge. So we take the original TED mesh, cut off an edge, we get prismatic elements, cut it again, so we get some cubes and prismatic elements next to the edge. And you see the elements stay long along the edge and they're very thin in the singular direction. And they get fine in all directions at the singular vertex. Okay, we set up the curl and mask matrix. For the preconditioner, we cannot invert the curl matrix. It's a preconditioner. In the bin-width iteration, we use the order 1 regularized matrix to get the preconditioner. Okay, now we have to realize this projection operator. Same with the curl. Okay, so the phase is the edge curl space. The edge curl space, what is the associate H1 finite element space? For example, you have a variable order. You need also a H1 finite element space with the corresponding variable order. Here we get get gradient. We get the corresponding H1 finite element space, and also the matrix representation of the gradient operator. If you have the coefficient vector of an H1 function, apply the gradient matrix, you get the coefficient function of the corresponding vector in the H curl finite element space. With this gradient matrix, we can realize the projection. In the gradient matrix, we compute its transpose. We compute the Poisson matrix by multiplying the mask matrix in H curl space with the gradient matrix and the transpose gradient matrix. This gives us the H1 Laplace matrix, which is singular, so we're regularizing it by changing one value. And here we're realizing the projection. So it's projection is identity minus gradient Laplace inverse gradient transpose. It's a residual, we have to multiply with the mask matrix again. We define the projected preconditioner, so the preconditioner, and then applying the projection. So if we always apply this projected preconditioner, we stay in the space orthogonal to the gradients by doing this coprojection. We can do this preconditioned inverse iteration, which we have programmed ourselves before, but now from the ngSolve core library. And we see the inverse iteration. It's plotting the approximate eigenvalues, 322. Okay, so there are, if you check the number of non-changing digits, you see that it converges pretty fast. There are reference values for this, and I think there are 5-6 digits accurate already. Thanks to this very strong geometric refinement towards the singular edges. And we can look also at the eigenfunctions. This is the norm of the vector potential, and you see these singular functions around the edges, which are very well approximated by these very stretched elements. Questions about? If not, then we continue. Okay, so far we have solved problems in one finite element space. Now we are looking into mixed formulation. First we're doing Darcy problems, mixed formulation for second order problems. So we look at the diffusion equation. So we have the second order equation with diffusion coefficient lambda, with Dirichlet and Neumann boundary conditions. This here is a primal variational formulation where the Dirichlet boundary condition is given by constraining u to the Dirichlet values on the Dirichlet boundary, and the Neumann boundary data is given in weak sense on the linear form. We rewrite it as a first order system by introducing a flux sigma, where sigma is lambda gradient u, or lambda inverse sigma is gradient u, and divergence sigma is minus f. Neumann boundary condition goes onto the normal component of sigma, so we see the normal traces are essential here. Dirichlet data stay here. Integrating the first order system with test function and integrating by parts to get divergence twice. So we are looking for a sigma in HDiff and then u. We don't have to differentiate the u, so we can pick u in L2. We have this mixed problem. First row, second equation, which holds for all test functions tau and for all test functions v. Or you can write everything in one equation. You can look for a sigma and u in the product space of an HDiff cross L2, and you add up the bilinear forms, and you get now a big bilinear form on the product space. Also all test functions tau and v in the product space. And that's the way we implemented it now in ngSolve. Okay, so first solving the primal problem. We have a source term in the volume. We have Dirichlet data on part of the boundary. We have Neumann data on some other boundary. Setting up a primal problem to check for the reference solution. Coefficient lambda grad u grad v. We set the primal grid function to the Dirichlet value at the bottom boundary. The linear form has the volume source and it has the Neumann data at all of the boundary. Homogenization, residual update of the solution, and we get the primal scalar solution, and the flux looks like this. Now we are solving the corresponding mixed problem. We have an HDiff finite element space, we have an L2 finite element space for the flux and for the scalar. The role of Dirichlet and Neumann data is now exchanged, so we say constrained boundaries are now the other boundaries, which have been Neumann boundaries before, are now the essential boundaries, and we use a Dirichlet keyword for specifying the essential boundary conditions. And the space is now a product space. We write by v times v to get the product space. The product space gives us trial function and gives us test functions, and trial functions we can unpack in Python as a sigma and u. So sigma knows I'm now an HDiff trial function in the first component of a product space, and u knows it's in the second component of the product space. Here we have to work explicitly with the normal. There's a special coefficient function normal in 2D. It's a two-dimensional coefficient function, and depending on the context, it gives us a normal to either to the geometry or the element normal, depending on the context where it is used. The bilinear form, now the big bilinear form from the mixed formulation, 1 over lambda sigma tau plus diff sigma times tau plus tau times u. Example, the linear form of the big system. We have the GFM, the grid function from the mixed system, where we can unpack the components into sigma component of the solution and u component of the solution. Before actually computing, we do some little games with the sigma and the u grid functions. For example, setting the sigma grid function as a function, setting the u grid function as a function, and looking at them. The sigma is something highly oscillatory. We're setting the x to the u part. Remember, we have chosen linear fluxes and piecewise constant scalars, so that's a piecewise constant approximation of the linear function. Okay, now we are solving the problem we want to solve. Setting the essential boundary condition for sigma. We have to specify a vector where you have the Neumann data times normal. We have to make it a vector, and it means we are setting the normal component of the sigma corresponding to the normal component of the vector function we are providing here. Same trick, residual, update of the vector, homogenization trick again and again. And if you compare the pictures, they look eyeball norm very similar to the scalar the flux solution and the scalar solution as we got from the primal problem. Flux looks pretty fine, as it's usual for mixed methods that the flux comes out much better. But the scalar variable, which is usually much easier, is only piecewise constant, does not look so nice. We can also compute the difference to the primal solution, and we see the error in the scalar and the error in the flux. Yeah. But I guess most of you know that you can do something about this. You can do a local post-processing for the scalar by recovering the scalar variable from knowledge of the flux. This equation says that the lambda gradient is a best approximation to the flux, and you want to solve this local problem, but this would be a singular problem on the elements. You have to fix something, you have to fix the mean values, and you say the mean value of u is the mean value of the post-process u is the mean value of the finite element u. You can write down this post-processing problem as a mixed variational problem with a recovered post-process u and the Lagrange parameter for the mean value constraint. The mean value constraint of the mixed value, the mean value of the mixed solution is already satisfy a superconvergence property. And when you do this post-processing, you get also the scalar variable plotted here of higher order accuracy, so the stress was order 1. The original, the stress was approximated as good as you can do with linear elements. The scalar was as good as you could do with constant order elements. After post-processing, you lift up the order of the scalar by 2 orders. Now the scalar is as good as it can be with second order approximation. And you see the post-process u is much higher accuracy. Okay, mixed problem, Darcy's problem. It's an interesting problem for getting used to mixed formulations. It has some applications in flux recovery, error estimations. It's a good model problem if you want to study fourth order problems with a similar structure, but technically more complicated. Yeah.
So when you're computing the matrix, when you're numerically integrating, can you use different quadrature for, let's say, when you're computing sigma tau?
Yeah, very good point. Example. Yes. Depends on how you write it. Where did I define the? Yeah. Okay, I say, okay, here I have a big bracket over all the terms and say 1 dx. I can give here the order here. Then I have the same order, then I have the same integration points for all components. However, if I break it up to several integrals like this, then it does the, okay, I want to remove this. Then it uses then it integrates all terms differently, and it will use different quadrature orders for the different components. Okay, what quadrature order is it using? We didn't talk about this. From the expression here. Okay, it has a sigma trial function and a tau test function. They belong to second order H-diff spaces. We get some second order triangular element. The finite element knows their order. And from the element order, we are defining the integration order. It works if you have mixed elements, if you have variable order elements, and for every element, it attracts the order from the finite element polynomial degree. What we can do is, if you say, I'm not satisfied, I want to see whether I need higher order, you can say, thank you. You can do this, and say, it's okay, do 2 orders higher integration. We prefer this instead of giving the absolute order. Since when we are playing, changing the order, then we often forget to change the integration order also. But with specifying the bonus order, if we change the order above or have variable order, then we automatically get also a bonus int order.
Okay, so this is still you're using Gaussian quadrature. Let's say if you want a trapezoidal rule here. Is that possible?
Okay. You can specify your own integration rule you want to use. You can declare an integration rule in Python. You can give the integration rule also to the dx symbol. Okay. For mass lumping, for example, trapezoidal rule. Then you can give an integration rule for every element shape. Then you can say on tricks I want to have this rule, on quartz I want to have this rule. Some more integration rules. Oh, that. Okay. Internally, it makes a difference whether we write it as separate integrals. It computes also the smaller element matrices just involving the sigma and tau. And sigma times v. If you give the integral over the big term, it always computes all terms for the larger matrices. So it might be a little bit more efficient if it splits the integrals to the blocks. Another popular mixed equation is Stokes equation. So looking for a velocity and a pressure. Velocity in a vector h1. Upper form here is gradient u, inner product with gradient v, or symmetric if you like. Divergence of the vector times pressure test function. We do the flow channel from this drag and lift benchmark from Schäfer and Turek. Meshing with curved elements for a good boundary approximation. Okay, now we have let's start with the Taylor-Hood elements, which are second order continuous element for the velocity and continuous elements for the P1 elements for the pressure. Velocity space is vector h1. Don't like Taylor-Hood. Second order, first order product space here. Stokes binomial form. So we can do it also in one. So x trial and test function. It gives us the trial function up and the test function vq. And we can break the trial function immediately into velocity trial and pressure trial function and velocity and pressure test functions. Now you see a capitalized gradient. Maybe some who have been using edgesolve for a while know about the confusion about is the gradient row-wise or column-wise. Some spaces it was row-wise, some arguments were column-wise. The capitalized gradient is always the row-wise gradient. Okay, vector h1 is like h1 times h1, 2 copies of h1, but it can do some optimization since it knows it has twice the same finite element space. For example, vector h1 can also define the divergence operator. If you do an h1 times h1, then you have to do x derivative and y derivative and put them together manually. If you have a vector h1, it knows it makes sense to talk about divergence, and it provides the divergence operator as a canonical operator for the vector h1. Okay. Set the Dirichlet values at the inflow boundary with the trivial harmonic extension to the correction, and we see we're looking at the absolute value of the velocity field. You see the flow is faster where you have this obstacle, and we want to see a solution like this. And for class, when teaching Stokes finite elements, you want to try out different velocity pressure elements. We now set up a function for testing for solving Stokes problem. We give a finite element space, a pair of finite element spaces, setting up Stokes, solving Stokes, and drawing the solution. Okay, again Taylor-Hood. Oops. Yeah. Now we used a space pairing of fourth order velocity, third order continuous pressure. Okay, eyeball looks reasonable. Okay, now we try P2 continuous elements for the velocity and discontinuous pressure of order 1. Okay, oops. Okay. Okay, it's good. So it's a bad pairing leading to a singular matrix, and the factorization realized that the matrix is singular, and it complained about it. Okay, we know the P2 P1 P2 discontinuous P1 pairing is LBP, in the sense of LBP, unstable. What you can do is you can do bubble enrichment P2 plus cubic bubble, P1 discontinuous. We can do this here, so we can use essentially second order spaces, but there's an order for the triangular faces to order 3. So we get the cubic bubble into the space, which works fine. Or you can do the mini element, which is P1 plus cubic bubble. It's also fine. Okay, you see it's a bit rougher. It's only P1. Okay, you can try the classical textbook element in this sense. Now we were solving up the Stokes problem as one big matrix, the whole system as one indefinite matrix. We can also build blocks for the individual matrices for the individual block, a matrix for the upper left block, for the A block, a matrix for the divergent operator. Now we do not build a product space. We have the velocity space, we have the pressure space. Now U and V are trial and test functions from the velocity space only. Now U knows I'm the trial function of an vector H1 space. Before, U was the trial function of the first component of a product space, which is a vector H1 space. So they are different objects. If you use the one from before for this setting, it might crash. We're building now the binomial form for the A binomial form for the upper left block. We're building the divergence binomial form called B, diff U times Q. This will give us a wide rectangular matrix. Now we have the individual matrices. Somehow we have to solve it. For the preconditioner, we need also a preconditioner for the L2 space for the pressure. Two components of the right hand side. We are setting the inflow boundary conditions for the velocity. And now we are building up a block matrix. Okay, the block matrix, upper left block, upper right block, lower left block, nothing here. A block diagonal preconditioner. a block vector for the right hand side, a block vector for the solution, and calling a minres Krylov space method for this block matrix for the block diagonal preconditioner, and looking at the velocity at this axis. You can do also stabilized methods where we want to use equal order elements, and you can do also so-called P1 iso P2 where you replace the P2 by a refined mesh and doing piecewise linear on the fine mesh for the velocity and piecewise linear for the pressure. You can try many of the classical elements in here. Yeah.
Could you explain the set order, how it's designed? How does it know that when you set order trig 3, it added 1 cubic meter, right?
Yeah.
What happens if I do set order trig 4? What's the rationale? How do you?
Okay, let's play with, where was it? There was the failing one. Okay, yeah. Okay, let's do a print v.end of.
You printed
capital V.
I think, yeah. Okay, now we have 5,000. If we are not doing this, yeah. Thank you. We printed anyway. Yeah. It's 5,000. If you do it 4, you get some 8,000. You get more internal bubbles. Yeah. So since the finite element spaces have orders for edges, for faces, for cells, you can have different orders for every node. You can set orders for every face individually. You can have on this edge 5, on this face 7. And when you set this order policies, then all triangular faces have order 4 for the face-based basis functions.
Okay. So if I put instead of trigger, I put segment, it will be an edge bubble.
Okay, let's.
I should understand.
Okay. Hopefully, if I set segment, now the segments are order 2. Now I update also the segments to order 4, and hopefully I get still more. Yep, I got more. Was not sure. Yeah. But it's the same as if you would set order 4 from the beginning. Hopefully. 17,000. Yeah.
Thank you.
Yeah.
Can I, since I'm less familiar with it, just follow up on that exact same thing. So when you start out, you have order 4 elements, vector h1, I guess that's, yeah, okay, x and y.
Yeah.
And trig stands for triangle?
Right, yeah, trig and quad and
so
tet and hex.
Since it's 2D, does that mean internal?
The internal, yeah, the internal order.
Okay, not on the edges.
Not the edges, yeah, only for the, so on every node, with node we mean edges, faces, cells.
Yeah.
We have basis functions supported on the faces.
Yeah.
Trig is a 2-dimensional object, so this goes to the triangular faces internally.
And so that's when you said once you've added to the triangular faces and segments, it's the same as if you had done order 4 to start.
Yes, yeah.
Okay, now.
Maybe you miss one of the elements you may have seen. So 14 rouge element is something where you have only the normal component, high second order, but the tangential component, first order. We are not supporting this. We are supporting elements we can map nicely from the reference element to the physical. If you have the second order bubble in normal direction, you cannot map from the reference element in it. Sorry, it does not fit naturally into the NGSolve framework. It's more tricky and maybe more. You can do it with some tricks.
You can do it with like 1.5.
Yes, yeah. If you
nothing you can't do with Lagrange multiplier.
Okay. Okay. We were talking about these mixed methods, and now we want to do hybrid mixed methods.
Is there still support for the bed computing and no element? The P1 is of P2.
Okay.
Is there still support for the P1 is of P2?
P1 is of P2.
Ah, yeah. You can do it also with information refinement. I was looking at the time and was skipping it. Yeah. It's okay. This hybridization, making the mixed system even larger, you make the HDIF, the Ravi-Atomar elements, which are normally continuous, discontinuous, and you take a Lagrange multiplier to glue it together again. Okay, now the sigma is in a element-wise Ravi-Atomar element-wise HDIF space, discontinuous between elements, and the V hat is a Lagrange multiplier for making the normal component continuous again. Looks like a bit upside like this, so it's making it even more complicated, more variables, breaking continuity and reinforcing it. But this hybridization is a very nice thing that you now can eliminate the sigmas and the u's. You can condense them out. You can go to the Schur complement involving only the facet variable u hat. And you end up with a positive definite system on the mesh skeleton. So these u hat variables are polynomials on edges, polynomials in the edge coordinate. Okay, this is a hybrid mixed formulation. How to do it? So the same problem as before. Okay, what we do is we build an HDIF finite element space and we put the discontinuous wrapper around it. So you can break every finite element space by this discontinuous wrapper. Then you have the same element basis functions, but also continuity constraints between elements is gone. You duplicate the degrees of freedom on all elements, just the connectivity is different now. The same basis functions, but different discontinuity matrix. The same L2 as before, and now we need the Lagrange multipliers on the edges between the elements, or in 3D the faces, or we call it facet if it's a codimensional 1 simplex. It's a facet FA space. These are now polynomials of order on all the facets between the elements. We have now a product space of these three variables. We're looking now at the range. So the first space component of the product space, range 0, the sigma variables go from 0 to 1120. The u variables go from 1120 to 1456. And you see the semi-open intervals. The first one counts, the last one is not included. Okay, what do we do here? Okay, so the enforcement of the continuity is a sum over all phases. On every phase, I look at the jump of the normal flux, test it with the Lagrange parameter V. We can rearrange this phase by phase integral by integrals over elements. We are integrating over the boundaries of the triangles, of just the normal component from the current triangle, which are the sigma ends are different from both triangles sharing an edge, but the Lagrange parameter V is a single valued test function on the edges. Okay, we are expanding the trial and test functions. You had this facet variable. These are all element-wise integrals, so the divergence sigma times V is computed element by element, it's the same. Now again we see this normal vector, but now we're using the normal vector in the context of an element boundary integral. We write this by dx, where dx stands for volume integral, but instead of integrating over the element, we are integrating over the boundary of the element. So this integral is now broken into the 3 edges of the triangle, or whatever we have, kind of boundary faces we have. We integrated sigma n, and n is the element-wise outgoing normal vector. Okay, we're using the BDDC preconditioner. BDDC takes as wire basket degrees of freedom whatever the spaces suggest. The broken sigma and L2 said, okay, we have only local degrees of freedom, so we don't have wire basket doves. The facet FA space, which are polynomials on the edges, take just the first basis function on the edge. And now we have to know we are using L2 orthogonal hierarchical spaces, so the first basis function is just a constant on the edge. So the wire basket of is a constant on the edge. It contains out all other degrees of freedom locally, and the remaining global system is a constant on the edge, the same type of degrees of freedom as if you use non-conforming P1 elements. And it has condensed true, I guess. Yeah, we set the condensed true. Yeah, in this branch we have condensed. Okay, this means we do this trick with the harmonic extension, the modification of the right-hand side. Solve for the Schur complement. The matrix which is built is the Schur complement matrix, so the matrix for the facet variable, which is now positive definite, so we can use conjugate gradients with the BDDC preconditional. And after computing the facet variable, we can recover the inner variables by the harmonic extension and inner solve. And we get hopefully the same. You remember the pictures, they look the same. Okay, this is the hybridization with the finite element spaces on facets between the elements, which we have to say we like very much in ngSolve, and they are getting now more and more popular, and you can do very nice things with them.
Johan, perhaps you can say something about why not vector of 2 and discontinuous HDiff?
Discontinuous, why not what?
You use discontinuous HDiff, not vector of 2, which is almost the same.
So it's okay, yeah. It's almost the same. It's not the same if you have curved elements. The mapping is different. Yeah. Yeah, the bases are also different, but if they maintain the same space, yeah. What else you want?
No,
okay. Curved elements.
Without curved elements, they're the same.
Yeah, if you do curved elements, then if the facet variables are of the same order as the hard-diff variables, then you still recover exact normal continuity. If you do one-to-one mapping of vector H1, then the spaces don't fit exactly together and you do not recover exact continuity. I think I said before, the lowest order piecewise constant on the facet is like the non-conforming P1. You may remember from finite element class, you cannot do a discontinuous P2 element, as with P1, it's singular, but you can do a second order or higher order hybrid mixed method without any problem. Sure. Okay, I wanted to say this. We can do discontinuous Gajokin method, and we can do hybrid discontinuous. We like very much the hybrid DG. Maybe I stop this. We can do fourth order equations with this Helen-Hermann-Johnson method. I think Michael is talking more about this tomorrow. If not, then not okay. If you want to do fourth order problems, H2 problems. Ah, yeah, good. One choice is to use discontinuous Gayorking method, where the functions are still continuous, but they are not C1 continuous, and use a discontinuous Gayorking method for the missing C1 continuity. You get a bunch of these element boundary terms, which you can hybridize also. And what you see here is a normal facet FA space, which is a facet, polynomials on the facets, but only in normal direction on the facets. That means you have it's a continuous function W and a approximation for the normal derivative on the element skeleton. And this, you have jump terms which are differentiated between the element gradient and the facet variable. Okay, no, very quick. It's a hybrid DG formulation, so we're integrating the Hesse term from the element against the jump term. This is a C0 DG. If you have seen it, you recognize it. If you have not seen it, don't worry. And that's one method to solving fourth order problems. That's a plate problem. So they have the vertical deflection of the plate, and we are plotting also the Hessian using higher order. So the Hessian also looks fine, and the XX component of the bending. But what's really the much cooler method is the Helen-Hermann-Johnson method, which is a mixed method. Mixed method similar as the mixed method for the flux, but now it's second order, so Hessian of the scalar, and sigma and tau are symmetric matrices. Okay, we want to avoid, we do not support C1 elements since it's a mess to implementing C1 elements, so we don't want to have the second, we want to have the H2 space here. What you can do is you can do one times integration by parts, so we're forming a divergence against the gradient. And this Helen-Hermann-Johnson uses now matrices tau, which have continuous n components. From the matrix, only from the, not the full normal vector, but only the normal component of the normal vector is continuous. What means that divergence is a distribution, and a distribution acting in tangential direction on the edge, and this distribution can hit the gradient of a Lagrangian basis function. So this duality pairing makes sense for proper finite element spaces. You have to compute these terms here, element-wise diff sigma times gradient. On the element boundary, you have to integrate the NT component times the tangential gradient of the. And the interesting thing about this is there are many publications in the 60s and 70s up to 80s. Then 25 years, I found no single publication on this Helen-Hermann-Johnson method, and the last 5 years, there are papers about this are exploding. Somehow, I believe it was too complicated to work with these methods in early times of finite elements. Even Nedelec, Ravier-Tomar elements have been too difficult for this time. How should people done matrix valued elements in the 60s? Now technology for these elements is here. You can work with them as easy as with Nedelec elements.
Actually, there's another paper that you should add. Bloom and Ronacher, 1990.
Is it? Okay, it's okay. 89. Your paper was
Bloom and Ronacher, 1990. They also have a.
Which year?
1990.
Okay, sorry, I missed it. Sorry.
Yeah.
With commodities, the stability was set for higher order. I missed this. Sorry. Yeah. And if you want to have the analysis for curved elements, you'll get Sean's paper, Mr. Arnold. The space to get this NN continuous matrix value we call HDiff-diff, since you can apply the robust divergence and another divergence. Scalar H1. This distributional divergence, element-wise divergence, tau times gradient, and on the element boundary you are integrating the tangential component of sigma of the normal stress vector with the tangential gradient. and you get with less work. You can hybridize them. It's a cheaper method than the C0 continuous HDG. It's very nice. You can map it also to shells, and these elements have a natural mapping for curved elements, and also to map it to manifolds. This you will see tomorrow, I hope. Some newer notebooks. Okay, we can do matrix-free operators. I come to it tomorrow. We can do periodic spaces for a while, but it has never been so well in the. It hasn't have in the Jupyter documentation. We do a unit square rectangle, and now we are naming left and right boundaries, left and right, and top and bottom. And we want to do periodic finite element spaces, so we identify the left boundary with the right and the upper with the lower in the geometry. And if the edges are identified in the geometry, you see this, then it's a mesh generator, meshes one side and copies the mesh from one side to the other side. So you have matching meshes on left and right and top and bottom. And you see the identification of the vertex top with the identification of the bottom vertex, which was not supported by our web GUI. But a recent feature for the web GUI is that you can plot your own stuff also. And with these few Python commands, we are plotting the identification of the vertex pairs here. It has not said either. So if you look to the online documentation, or if you browse down to the very end to the appendix, you have an appendix on web GUI. There you find some documentation for the web GUI, but you do not find the documentation for the easy things. You find the documentation for the fun stuff you can do with this web GUI. Find some ideas down there. Okay, what we want to do is we have a mesh where left and right is identified. We build an H1 on this space, and now we have a periodic wrapper, which takes information that the vertex from left is identified with the vertex from right, the edge from left is identified with the edge from right, so it contains a space such that you have the same values on the right side as you have on the left side, and top and bottom. So I have a peak somewhere here in the upper right corner. Since the functions are continuous, the same identical top and bottom, the peak also expands to the bottom since you have a 2 times periodic domain.
Well, I have a question here. So you have a periodic mesh.
I have a?
You have a periodic mesh, and then you have a periodic finite space.
Yeah.
I think you have periodic mesh, then you define finite element space. It will automatically be periodic. No.
If you define what?
But it's not.
If you define what?
So if you have a periodic mesh,
remove the periodic.
Okay, good point. Okay, we have different okay, we have different vertices and the coordinates are different. And the degree of freedom is assigned to the right vertex, and the degree of freedom here is assigned to the left vertex. And only with this periodic wrapper we map the right degree of freedom to the left degree of freedom. We could also put a phase shift into. Then we need different values left and right for quasi-periodic functions.
I saw that you wanted to draw the line in purple, but I'm struggling to see purple.
Yeah, you need a better projector. Yeah. Let me continue with periodic for the 3D. And I think it fits to the coffee break, so we have a piece of cake, I hope. Okay, something like this. And I have a phase F1 here, and a phase F2 here. And I identify the left with the right. So we can identify phases from here to there, but if they are not opposite to each other, but somehow other transformed, they made this by drawing a rectangle in cylindrical coordinates, put the work plane in cylinder coordinates, I revolve this rectangle to get this cake. In the identification, I say the phase F1 is identified with the other phase, but and needs its rotation by 30 degrees to get a point from one face to the other face. And you get these purple lines also here. You see it better if you turn off the this is the identification form in purple. And solve on this domain. We have a source here, which is also transported by periodicity to the other side. One application which comes up with computing is computing band gaps, so photonic crystals. So we're solving this, computing this phase shift. So k is the wave vector in space, and omega is the frequency, and it ends up in a, if you do it from k to omega in a linear eigenvalue problem, from omega to k in a quadratic eigenvalue problem. I just want to run this. We're going the quadratic eigenvalue problem case from omega to k, and I only want to be computing the k eigenvalues, and then to getting the full band gap, we do this with reduced basis method. So we are projecting the space into a low-dimensional space, just computing a few snapshots. Okay, I'm speaking very fast, and I just want to show you the final picture. We computed a reduced basis model by this multivector, projecting all the matrices to small matrices. Now running many frequencies for the small problem. You see the bands here. We are sampling in the frequency space, so you see there are just a few dots of these bands, and it's very flat. You see this vertical line also, the connection between the bands. If you go to the imaginary part, you see the imaginary part, but if you plot the complex k vectors, you see the connection of the bands via complex numbers. You see here the propagating bands. And if you have a finite number of unit cells, you see the damping from the imaginary part here. And have shown the cake. I think it's now a perfect time for making the coffee break.
Question?
Where's that last notebook? Where did you bring that up from? I couldn't find it on the index.
Ah.
Oh.
Okay.
Thank you. It's as a link in there.
Okay.
Cool.
Yeah. Very base. Yeah. at a very young age into NGSolve, and is now one of the leading developers sitting in Göttingen.
Yeah, so in the last time you said I was doing NGSolve for 20 years, so 20 years ago I was still at high school, so okay, but yeah, but still a long way, and we've come quite a long way since the last, whatever, 5-6 years, since the first user meeting. So I think the material that we have is quite extensive now. And yeah, you saw that Joachim also had to skip some stuff. So I want to anyhow still do one of the things that was in on the second part on discontinuous Galerkin methods, because I will also relate on that later on. Okay, so discontinuous Galerkin method probably is known to you, most of you. So the idea is that we use discontinuous finite elements now, so L2 function space. Here we do the scalar setup only, and yeah, here are examples. So like the interior penalty formulation for diffusion, for Laplace equation, for the plus operator with the usual jump and average operators involved, or you can also think about convection. We will also do this in a minute. And the question is how to do this in NGSolve, yeah? Because obviously now you have a non-local, so we have neighbor communication, and this is something that I want to address here. Okay, so we start with a finite element space L2 here, and what you see now, what's new is the flag DG jumps equal to true. Because in NGSolve, the information which degree of freedom couples with which degree of freedom in the sense of setting up the linear system, the sparse matrix later on, is already kind of configured or defined through the finite element space. And usually, so we saw this when we discussed also static condensation, an L2 space has only local degrees of freedoms, and it only couples with other functions that are supported on that element, so which are also defined there. But of course, in a DG setting, think about the simplest case, we have piecewise constants. You want to have these two constants communicating with each other. Okay, in order to kind of reserve the corresponding non-zero entries in the matrix later on, we have this flag DG jumps for this space or for any other space. Yeah, so it just essentially says not only take care about couplings within one element, but also think about coupling through facets. Okay, so yeah, and then you can define jumps. For example, here jump u is u minus u other. So this is another keyword that we get to know here. So this is exactly as you would read this. So if I'm on one element or I'm on a facet, then I have kind of one primary trial function u, and the secondary is kind of the u other, so the neighbor of that current guy. Okay, and then here we form jump u, jump v, average of the normal derivative of u, average of the normal derivative of v. Okay, so with that we are able then to define the interior penalty formulation as you have here. So it's just some busy terms, but it's not that fancy. So as you saw this before, this is the usual symmetry parts, the consistency parts, and the stability part. And you can put this together and assemble a matrix. Now, so this is, as you know, this. So this is now the diffusion thing. Correspondingly, we can set up the right-hand side, just integral of 1 and times v on the domain. We can invert this and draw this, and we get kind of the solution for the Poisson equation on the unit square. So something that we are used to, but now it's with a DG function. And I'm actually not. I think it's order 4, so you'll probably not see so much of the discontinuities. But okay, we can perhaps briefly repeat this to see that obviously we can also deal with. Yeah, so if you zoom in a bit, yeah, you see that's indeed a discontinuous function here. Okay, good. Now let's talk about the matrix, and then what I said before, we have the flag DG jumps. Here we don't have the flag DG jumps, and now I just assemble more or less a random matrix, so mass matrix. And what you see now here, if you compare the non-zero entries in your matrix, so a.mat.nonzero entry A was the matrix from before, you see that you have 756 non-zero entries, while if you just do the L2 space without the ggjumps flag, you just get 216 non-zero entries reserved. And this is, as I said, because there's no, there's only the coupling from within the elements that you see. So actually, the matrix that you get here is a block diagonal matrix because there's only locally coupled effects here. Okay, so let's see what else we can do. This is now the convection. So if we think about solving convection problem with an upwind discretization, we want to implement this bilinear form here, where you have essentially the volume part of the convection. So there's the volume integral missing, but okay. And then we have from partial integration, we have the boundary Bn times u, and the numerical flux choice is kind of the usual, take the upwind choice here. Okay, let's see how we implement this in the script. So we have here velocity field B. So it's some velocity constant going from left to right, from bottom up. And now we have here the coefficient function if pos, which takes 3 coefficient functions. And this is kind of now a discontinuous decision. Yeah, so the first coefficient function decides if I return the second or the third argument of that function. So if b.n, so the velocity field times the normal, so we think about the normal of the current boundary of the element that we are at. If this is outgoing, so bn is greater than 0, that means the flux is outgoing at that phase, then we take u, so the local version of the unknown. Otherwise, we take the other one. So we always take kind of the upwind choice, yeah. So the choice where the flux comes from. And then the convection term is here. So you have the volume term. This is just gradient, partially integrated part. So b times u gradient v with the minus, and then the boundary part here. Now with a skeleton formulation. So skeleton is now the keyword that we have this sum over all facets in the mesh, all interior facets of the mesh, and then we integrate over the facets. This is kind of done with a dx skeleton true. And then we have this guy here. So u upwind is this upwind choice that we defined above. And then we have essentially the test functions from one side and the other. That's why we get the jump there. Okay, we can then set this up, solve it. Now we have a convection diffusion, so we put those together and solve for the convection diffusion equation. Okay, with order 1, we don't see so much. Probably gives us a boundary layer, so let's see how the boundary layer looks like if we resolve it a bit better. Okay, we see deformation is not too much, 10 times GFU. Okay, mesh, sorry. Okay, deformation on. Hopefully now we see something. Okay, so flow from left to right pushes this to the boundary. We have boundary conditions there imposed by the Nietzsche or interior penalty, however you want to see this. Okay, so this is DG, and now we also saw this partially in Joachim's part. DG is quite expensive when it comes to solving linear systems because of all these couplings that we now introduce with the DG jumps part. And to solve similar problems more cheaply, you try to avoid actually this DG couplings, the DG jumps. And one way to avoid this is by using this facet unknowns that we have in hybrid discontinuous Galerkin methods. And for that, kind of this is now, we'll be a bit faster on this because that's something that you similarly saw already. So the idea is now that on top of the L2 function that we have, now without the DG jumps flag, we introduce the facet V space, so the facet functions, and now formulate something similar to the interior penalty formulation from before, but now we replace the jumps. The jump is not current view, so u minus u other or v minus v other, but it's v minus the facet version of that or u minus the facet version of that, and similar terms. So yeah, so this we can also do similarly for the upwinding, so for the convection part, and then we get overall essentially the possibility to solve these things. And again, we can do this with static condensation or not. So this is as we've seen this before. Yeah, the quality of the solution is very similar to the DG solution. There's no drawback in that regard, but the advantage that we have static condensation available, and so not the burden essentially of this DG couplings. Okay, so there's something on protected jumps, so you can even improve on the facet unknowns a bit. I will skip this for time reasons, but okay. All right, questions on this DG jumps or something? Okay, so then I will go to the part 3 of the tutorials. Yeah.
When you have a facet, oriented facet, the normal is fixed, and then when you say u minus u other, you're going from the element from which the normal points?
Okay, so in the mesh, when I'm at a facet and I have this facet integral, then there's always one element that is the one, and then the other is the second. You don't know this a priori, that's a question. But you should formulate this such that it's not important. Okay. So, so I wouldn't know that there's any mechanism that gives you any obvious orientation at that point. Okay. All right. So now, so in this part, we want to go to time-dependent nonlinear problems, and I want to start with a parabolic model problem. Okay, and the question is kind of how can we solve the heat equation now, or actually the time-dependent convection diffusion equation here. So we want to solve this this problem. So we have a given suitable velocity field B, so that the convection is given, and yeah, we want to solve that problem. Okay, so yeah, we import some stuff, nothing fancy. So you have unit square as you would expect. Oh, not yet, sorry. Okay, sure. We have this here, so just a unit square, nothing fancy. We take a H1 for an element space with zero boundary conditions. We already have a variable time and a time step dt of 10 to the minus 3. Okay, and we have some velocity field that essentially is kind of a vortex going around in the unit square. So what we now want to do is we want to do an implicit Euler time discretization. And for that, what we want to form is essentially mass matrix plus delta T stiffness matrix. And this is kind of what we want to learn here. So how can we do this in ngSolve? And what we do here, of course, we could put this in one bilinear form, assemble that. But here the idea is that we have these two different matrices by getting the two different bilinear form assembled. And the question is, how can we put this together to one linear combination of these matrices? Yeah, so this is the implicit Euler formulation for that problem. And we want to do in one time step, essentially, we want to solve this m star, so this m plus delta Ta times new time step un plus 1 equals to m un plus delta Tf. Actually, we prefer a bit the second formulation, so I have to just restart this. The formatting is off because I started with the wrong size. Sorry. Okay. It is how it is. I don't like this. Okay. Didn't work. Whatever. Okay, so the idea is that we prefer this incremental formulation, where essentially just formulate this in terms of the increment un plus 1 minus un. This facilitates working with boundary conditions, because if you have constant boundary conditions in time, then essentially you have homogeneous boundary conditions for this increment. Okay, so how do we do this? The idea is that we create a new matrix here, m star. So we get this by mmat create matrix. So this will have the same sparsity pattern as the underlying matrix mmat. So what we see here is essentially doing exactly that. So we see how many non-zero entries we have in the matrix mmat, so the underlying matrix, the amat, and the m star. matrix, and all have the same number of non-zero entries. And you can also check that it's actually also have the same sparsity pattern. So if you take a careful look here, you will see.
You can make it a bit bigger.
Yeah. But okay. Yeah, whatever. So these are the same, and this is kind of important if you now want to do this. The next thing. So now we want to add up the matrices, and we will not kind of add two arbitrary sparse matrices to each other and get a new sparse matrix with a different pattern, but rather we assume, or now we make sure that we have the same pattern, and just want to add up the data that is in this that is in the matrix. Okay, so the idea is here that we can access the data, so all the non-zero entries in the matrix linearly by calling this as vector for a corresponding matrix. This is exactly what we want to exploit now. So what we can do is essentially we just make a vector addition here. So we add the data from the M matrix plus delta T times the data from the A matrix and write the corresponding data of this M star matrix. And this realizes now this M star matrix, and I can take the inverse of that to do the time stepping later on. Okay, here's the setup for the right-hand side. The setup for the right-hand side is nothing special, so just the corresponding linear form. So it's this type of right-hand side. All right, we set some initial conditions. These are those, also not too much to say about this. And then here's a time stepping. So the time stepping is we set some initial conditions if we want, or we continue with the recent version. And then here is essentially the important line now. So what we do is for the right-hand side, we have minus delta t times a times un, so the old state, plus delta t times the source vector f. This gives us the residual, the result of this operation. Note that this is not a vector at this point, it's just a dynamic expression of this corresponding part, which kind of can be evaluated as a vector, which will be when we kind of need this, when, for example, now applying this here, this m star times this expression here. Okay, this then gives us the update, the increment. We directly add the update on the old vector, so that means we get the new state here. Okay, so this is what we define as a time stepping function. We can now execute the time stepping function and draw the solution. This is essentially what you get out of this. Okay, so we have this vortex of the initial conditions are moved and there's some source, so it looks nice. Yeah, so okay. All right, so yeah, so then in this unit I will not continue further, but there's more information if you're interested in using an iterative solver instead of using the direct solver here, or if you want to have a time-dependent right-hand side data or time-dependent boundary data, or if you want to kind of extend from implicit Euler to something higher order Runge-Kutta schemes. Okay, any questions? Okay, cool. Then I will also skip 3.2 for time reasons. Let's see if we have time later on, but rather skip to nonlinear equations first. So now we want to solve nonlinear problems. Okay, and this was too fast. Okay, so here's a simple example. Yeah, so we have Poisson equation, reaction term with a nonlinear reaction term 1/3 u cube here. And we want to solve this. And the question is, how can we do this? And of course, you might think about the Newton method at this point. And yeah, you could do this on paper. So think about the Newton method, write down how the Newton's method looked like, how each step would look like, and then kind of implement the corresponding linearization, bilinear forms, and so on. But NGSolve is very much capable of doing some symbolic computations, as you already saw in the introduction on coefficient functions and so on. And kind of this power can also be exploited to also put this into the solution of nonlinear PDE problems. Okay, and this is what we're going to consider next. So, sorry, I didn't mention what, again, unit square, so no surprises here, that we want to solve. And here now, kind of the corresponding nonlinear formulation would be the formulation, the variation formulation. You have a semi-linear form here that kind of is a weak formulation for your problem. And you want to have that this, of course, vanishes for all test functions v. And we use now a bilinear form in NGSolve to describe this. Yeah, so the bilinear form is not necessary, as you see here, that does not necessarily need to describe something that is indeed only bilinear, but it also applies as, let's say, semi-linear form. Okay, so we put this expression here, so you see that the trial function now appears in a nonlinear fashion at this point. And now what can we do with this? Yeah, think about the Newton's method. What do you need to really carry out the Newton's method? You need to evaluate the operator at a certain state, so a of u, which in our case would be a linear form, and we need the derivative, which actually becomes a bilinear form for us. And in order to get this, you have two functions in NGSolve for your bilinear form. The first one is apply, so you can put in a current state in terms of its vector. So the grid function vector, the vector of the grid function corresponding to the same corresponding finite element space. If you call the apply, you get the corresponding linear form, and the result is kind of like assembling the corresponding linear form that you have there. Then you can also get the corresponding linearization bilinear form, so the bilinear form that you get after linearizing around your state vec here. So the same story, you provide the corresponding vector of the grid function and you get a matrix with assembled linearization. Okay, so under the hood, what happens is that NGSolve takes this corresponding expression in your integrals and does the symbolic differentiation that you need in order to get the right derivatives for that. Yeah, so taking the derivative of, in that example, of the nonlinear part that you have here would yield this expression here. So u tilde squared times w times v, where u tilde is a state around which you linearize, v is the direction in which you linearize, and okay, v is obviously the test function for the problem. Okay, and then with that, the Newton method looks like this, pretty standard. Yeah, so you linearize around the current state, so that gives you the linear equation here, a of ui plus the linearization dA ui times the delta for the next step. So that means if you want to solve this, you need to evaluate this linear form a of ui. You need to set up the linearization matrix bi and then solve for the corresponding increment. You do this until you meet a proper stopping criteria. So this is how it can look like as a simple function. So the important steps here are these two lines. So we have a.apply, which give us the corresponding linear form in terms of the vector, and then we have the matrix a-assemble linearization, and this results in a.mat being the corresponding linearization at that point. And then we can call the inverse and apply this on this result to get the update and so on. So this is what we can do. Now we do this for the example and we see, okay, Newton iteration, as we would expect, converges pretty fast with a few iteration if it properly converges. And yeah, that's what we get out here as well. So this is kind of the solution to this cubic nonlinearity. We can also use the multi-dim again. So this is what I didn't discuss, but what I did here in this Newton method. For each iteration, I allow a callback, and the callback in this case adds the current iteration state as a multi-dim instance. Okay, and that kind of is something that we can now explore here. So we have essentially the initial given data is this one. It's hardly visible. It's different from 0, but not too much. And then after one iteration, we get this, and then yeah, 2, 3, 4. You hardly see any difference. Okay, good. So there's also something built in NGSolve, so you don't need to write your own Newton solver every time. So there's NGSolve solvers, which also ships the Newton. So you can ask for this. we have the corresponding arguments that do the same trick that we did. A bit more sophisticated, so there's some damping available, yeah, so you can set a damp factor and so on. But essentially, this is the same. Yeah. And yeah, as you see here, also you get the same result. After 4 iterations, you get convergence for the same type of problem. Okay, so I will skip the trivial example. So you could also do something just on a scalar. So perhaps the new thing here would be that we have something called a number space, which is just R, yeah, so which is one number on the whole mesh. And for that, we solve something that you can really comprehend and repeat with pen and paper. More interesting example, however, is doing something like stationary Navier-Stokes equations. So here's Navier-Stokes equations. We use directly boundary conditions everywhere. That's why the pressure is not well defined if we don't add this additional scalar constraint here that we have put on top here. Okay, the domain is unit square, and here's a setup of the problem. Note that here again we have the quadratic nonlinearity in here. Okay. Yeah. Good. Then we set some boundary conditions. We solved the driven cavity example. Okay, and we get this result. So this is initial value, and then after some time, we see the convergence pretty fast. So hardly any differences. You see small differences after 2 and 3 iterations, but then it converged to this solution. Okay, in this case, we can change the viscosity and make the viscosity smaller to make the problem a bit more challenging and interesting. You see, okay, now we need a few more iterations, but okay, so far this is still not too challenging. Now I'm a bit, okay, but yeah, okay, you can take a look at it anyhow. So we see that then we now get obviously more influence of the convection, so it flows more driven to the right, and that we repeat this now for Reynolds number 1000 approximately, and now you see, okay, Newton does not converge anymore. Yeah, so you get garbage after each of the iterations get always worse. So so what can we do? Now we could, for example, try a damped Newton here. This is what we do. And for that, we use the Newton that is coming from ngSolve. We provide a damping factor. Yeah, and with this, we see now, okay, slowly, but it converges. Okay. And then we can draw the solution, and we see, okay, this looks okay now, right? So this converged to something. Okay, good. So this would be it about the nonlinear solution. Any questions on that? Yes.
In the Newton's method, the first variation, the derivative of the inbuilt function computes itself.
So there's the sample linearization. Sorry, say this again. So the matrix that we need here, this A mat. The result of that is computed here in the assembly linearization, and this is based on symbolic computations based on your integral expressions.
Right. So then you're assuming that the function is smooth.
Yes, exactly. Yeah, sure. That's if you have something that is not kind of obviously doing the right thing there, then you should do something manually. But if everything is kind of offering the regularity that you need, then you can just use the facilities from ngSolve. Yeah. If you need to do something special, then you have to do this yourself.
So that's getting an analytical expression then, basically?
Exactly, yeah. Exactly. So this is based on things that Jay also discussed, where you have kind of the derivatives of coefficient functions with respect to other coefficient functions and so on. Yeah, so we can derive the coefficient function, which includes the trial function. We can derive this with respect to the trial function itself. Okay, so in the next unit we want to do something similar. We want to do now nonlinear minimization problem, and this is similar to the previous unit, but now we start rather with with an energy functional E of u that we will formulate also as a symbolic expression, essentially with a variation integrator and energy solver. So the concept is a variation here, and the idea is now that that we want to have that the derivative of that kind of gives us derivative of that being 0 is kind of the stationary point, which actually gives us kind of the nonlinear equation that we saw on the previous slide. So the idea is now that we can use energy solve. We just provide the energy that we want to minimize and not the expression in that form. So one step earlier if you want. Yeah, so if you, for example, consider this problem, then taking the derivative of that with respect to u, we end up exactly with the problem that we had on the previous slide. Okay, and the nice thing is now that we can put this in the form of the energy functional into energy solve. Okay, so here we take H1 space, u is a trial function. We don't need a test function in this form, and we have now here a plus equal variation, and then you put the energy functional here. Yeah, so you have here 1/2 gradient u, so normal gradient u squared, plus 1/12, and then u to the 4, minus right hand side 10 times u dx. Yeah, so you put directly that expression there. Okay, and then what energy solve essentially does, it gives you something that is equivalent to what we saw in the previous unit. It essentially solves for the problem of that corresponding PDE. You do the Newton solve, and you also get A apply, A in the A assemble with the same results as we had before, with the convenience of not providing more than this variation expression. And so this is the same algorithm as before, with the only difference that we now have also available something called energy, so we can actually quantify an additional measure for the minimization problem. Okay, so if we try this out for the previous problem, then we also get the convergence after 4 iterations. No surprise here, but now on top we have the energy functional that we can use to evaluate the quality of the result. Okay, that's also perhaps skippable. It's the same example as before, so let's skip this. Yeah, again, there's also something coming with energy solve, so you can call the Newton minimization on that. Okay, let's get to a more interesting application. So nonlinear elasticity. Here, the energy is this expression, which is much more complicated. So for deformation V, we essentially get this type of stress-related expression, which is obviously nonlinear with this neo-Hookean law here. Okay, and then what we do is we consider now a bar like this, so lengthy bar, which is fixed on the left-hand side. There's gravity on the remainder. So there's a force acting. So this is the force, and here are some constants for the material of this corresponding bar. Okay, so this is now how we put this energy functional into energy solve. So we can really just write down the straightforward expressions of this integral and put this into the variation guy here, because this is a complicated expression. It also is worth kind of using the compile, which kind of makes the expression more efficiently available for energy solve. Okay, so that's what we can do. We also need to be careful here. So in this example, if we would directly apply Newton iteration, it would not converge. So in order to get good initial values, we will kind of increase the load step by step, starting from 1/50th of it, and then incrementally increasing this up to gamma equal to 4, which is a factor in front of the load vector. Okay, and this is what is done here. So in each step, we solve the nonlinear minimization problem. We stored this in the multi-dim vector that we then use to visualize on this slide. And this is kind of what we now do. Essentially, we animate the 50 iterations one after another. So we have the nonlinear elasticity when the load goes from 0 to gamma equal to 5. Okay, yeah, I think I'll skip also this. So there's more examples. I think 2 more examples in the supplementary part of this. I would rather ask if there are questions until this point on that unit. Yes?
What is the dot compile method that you have in the variation?
Okay, this is what Jay also talked about. So every coefficient function has an evaluation tree. And with the compile, you can kind of, or we can try to optimize that tree. Okay. Yeah. And this tree is important in everything, in assembling, in evaluating integrals, whatever. And yeah, okay. Good. No other questions? Then we can continue. Yeah, I will do this. So in the beginning, I was a bit harsh on DG methods, claiming that they're always pretty expensive. But this is essentially when it comes to solving linear systems. They're expensive because of this additional couplings. However, in cases where you're more interested in operator applications, they're not necessarily that expensive. And this is something that we want to discuss in this unit. So operator applications with discontinuous Galerkin discretizations. Okay, in this unit, we will start with linear transport. So what we want to do is we want to solve this unsteady problem here. So you essentially just have mass matrix times time derivative and a convection term with a given velocity field B. Okay, so again, we define, we import libraries, define geometry. It's just a unit square. So with that kind of resolution, okay, and we want to apply essentially an explicit Euler scheme here. Yeah? So the simple thing that we could do, and I also have fixed the resolution, I think a bit higher than in your case, and I also use order 5 here because we want to do some timing measurements in the following. Okay, yeah, so that's why the numbers here are a bit different than they might be for you, but if you're interested, you can also increase the resolution to make it more interesting. Okay, so, all right, so we prescribe a velocity field. The velocity field is this one. It's, yeah, it's essentially just a flow going like a snake or whatever from bottom to top. And we want to transport some essentially given boundary conditions in time from bottom to top. Okay, so what we do is, again, we use an upwind discontinuous Galerkin discretization. So that's what we saw also before, but now we treat this with explicit time integration. Yeah? So there will not be any linear system involved that we need to solve except for the mass matrix. But for the mass matrix, we have a block diagonal matrix, and this makes it kind of cheap. Yeah? It's not really solving. It's not in terms of cost. It's not related to really solving sparse linear systems. Okay, we fix the time step. Yeah? So this is here roughly estimated that it works for the explicit Euler scheme. Yeah, what we have to solve in each time step is this here. Yeah, so we have a mass matrix, un plus 1 is mass matrix un, and then we have the convection operator and some right-hand side term. Okay, the right-hand side term f here is coming essentially from the boundary conditions. Yeah, so if we do the upwind scheme, then where the flow is coming from the boundary, that will prescribe the boundary conditions. That's kind of the data that we prescribe here in the F. The remainder is in this convection operator. Okay, so now we want to compute the application essentially of the convection operator, which in this case is indeed bilinear, but we don't want to assemble any matrix there, because that would be already too expensive. So what you can do is you can set up a bilinear form and set the flag as a non-assembled true. So here the idea is the C, so the bilinear form will act only in terms of a linear operator and never reserve storage or something for a sparse matrix. Okay, that's what we do here. So we have a bilinear form, and now the bilinear form has the upwind DG parts, the volume parts, the boundary parts, and here we use the version with the element boundary. Yeah, so we have the upwind flux times test function. And now we do this essentially on the boundary of each element, we will get the corresponding integral. Okay, pretty straightforward. And okay, so now we have a grid function. We have we can apply the operator. That's perhaps something to discuss. So the matrix C we set up with a non-assemble flag. So we claim we don't have a sparse matrix, and indeed we don't have a sparse matrix, and still we can use c.mat to get the corresponding linear operator. Yeah, so c.mat times a vector gives us kind of the same result as if we would assemble the matrix and then apply the matrix, but actually we're not doing this, we're computing these terms on the fly. Yeah, so no memory, or no large memory involved in these things here. Now, if I would just set the bilinear form up without this non-assemble flag, then you would get this. Yeah, you would get essentially an error. Matrix is not ready because the default behavior would be expecting a sparse matrix to be assembled before using it. Okay. So now mass matrix. We haven't discussed this yet. So also for mass matrices, for DG spaces, we actually don't want to set up a matrix, but rather exploit that we have a block diagonal matrix, and in many cases, and in most cases, due to this choice of bases, we even have diagonal matrices. And this can be exploited here. We also just want to have the linear operator related to either the mass matrix or the inverse of the mass matrix. And indeed, this is kind of what you get here. So we have a finite element space. You can ask for the mass matrix with a coefficient here 1, but you could also have some coefficient there. And then you call the inverse matrix. But this is now the base matrix that comes out here. So it's a linear operator. But in this case, it's not having a sparse matrix in the background. Okay, so here's now the time loop. So let's take a look at the important stuff on this slide. So we have essentially let's say here the steps. So we have the old state GFU back. We apply the convection operator. We apply the inverse mass matrix from the left. And this is kind of the update that we apply to our state up to the sign here. We do this now. This is the explicit time step. So this is essentially these two lines giving us one explicit time step. And we do this until we reach the corresponding final time. Okay, so here we solve this, and now we take a look at the time. So it should be something about 15 seconds or something, I guess, if I recall correctly. So, okay, let's see. 13 seconds, okay. And here's kind of the result. Now also using the multi-dim again. Yeah, okay, and you see now there's a boundary condition, non-zero, so there's two bumps, and they are now transported from bottom to top. Yeah, it's kind of behaving a bit wavy. This is essentially the interpolation of the multi-dim states that is done here. So of course it should be a bit smoother. This is 60 virtual height. So this is how much space the web UI widget gets here. So this is that it's not filling up too much or more or less. Yeah, so if I can make this smaller, then you have 20 VH. Yeah, okay. These are the things that I learned yesterday, and so.
You learned it yesterday.
yeah, we played quite a
feature exists since 2 weeks.
Actually, yeah, so it worked before, then it didn't work, and whatever, it works now. Okay, so this was based on the facet formulation. We can do the same with the skeleton formulation, because of course the rationale is that if you now run over facet twice, because you're doing this from both sides, this might be slower. So let's see, we do the same now with the skeleton formulation that we also saw before in the other unit. So perhaps one thing to mention is here that we can do the integral over facets with the dx skeleton true. That means these are all the facets that are in the interior of our mesh. And I also have boundary facets, and this I get with a ds skeleton true flag. I can also use here these region descriptions so like as before. So for example, here for the inflow and outflow regions, I can also use separate integrals if I want it. Okay, so in that form, we get this formulation of the convection operator, which is equivalent to the previous one. So we just take a look at this, put now the new C mat, so the new convection operator, in here and see if this changes the time measurements, and if yes, how much. So yeah, it's a bit faster. I think, what was it, 13 seconds or 12 seconds before, now it's 11. But we can even do better, and the idea is now that for both of these formulations we still have to do quite some communication from one element to the other element. And the idea is now also to kind of reduce that by the use of what is called here the trace operator. And the trace operator essentially does the mapping from the trace of our final elements from the discontinuous space to a trace space on the facets, obviously. So the idea is that we can create a facet space as V here, and we build a product space of volume and facet unknowns here. And we now have the trace operator, and VT, so the volume space, has this trace operator onto the VF space that we can set up here. So this is again a linear operator that represents kind of a matrix operation from the number of unknowns of my facet space to my from my volume space to my facet space. Okay. What it does is essentially it takes a trace of the corresponding discontinuous function and actually adds this up, because of course on one facet I will have two different values available, and we'll just add this up. And now the idea is that I formulate the convection application in terms of the local unknowns that I have and essentially the traces that I computed before. And so I can apply this the straight operator as you see here. So for grid function living in the facet space, I can just apply trace times the GG function and get the corresponding sum of traces here in this case. Okay, to make sense of that, we will split the previous formulation into three parts. We have the volume parts again, we have the interior facet part, and we have some inflow boundary parts. And this will now involve the facet and the volume space. So for the first part, we have now a bilinear form just on the volume as before, so nothing special. Here we now have a mixed bilinear form, so a bilinear form involving as a trial space the volume space, the product space of volume and facet, and a test space just the volume space. Okay, what we have here is now, we have to think about this carefully. So we have now an integral over all element boundaries. Yeah, so this is on purpose now. We want to stay local. We just want to have the information from the volume and the collected facet information. We don't want to have you and you other. We don't want to involve a direct neighbor now. We get the information from the neighbor in the following logic. So we want to compute something like my value or the upwind value, so the neighbor value, and I can do this following trick. So UF minus U here is UF is the sum of you, me, and you other, so me and the neighbor, and U is the local view is me. So what I get if I compute UF minus U, I get the value from the other that I stored before by taking the trace operation. This works on interior facets, and on the boundary, the facet value is u me anyway, because there was no addition from anyone else. So in this case, UF minus U is just 0. And that's kind of the trick that we use here. So we have now the if pos, so the upwind choice. If Bn is greater 0, then we would take our local version. So this is the UT, so this is the kind of, if I do upwinding, then the local version is the right on the outflow. But on the inflow, that's the third argument here, there I want to take the U other. Yeah, but now I encode the U other in terms of this UF minus U formulation. Yeah, so this is kind of how I have this. So with that, I have all the communication to the neighbor done. And the third part is only setting up the boundary data influence in in my case, and then put this in a standard linear form. Okay, so now let's see how the operations work. What we still have to do is we have to include taking the trace before we do the convection operation in this that we had before. And here we can use the embedding operation. So the embedding is the following. So if I have a product space and I just want to essentially set up a matrix like here, so I have an identity on one block and a 0 on the other one, then I can do this with the embedding operator. So the embedding operator here takes essentially has the size or the height of the whole product space, but it has the width only of the first subspace and correspondingly addresses the corresponding unknowns here. So we have the embedding of the volume and the embedding of the facet, and what we now hear is embedding of the volume unknowns plus the trace operation and then embedding this into the product space. Now, so we can now put in on the right hand side a volume vector from the volume space, get a corresponding trace vector from that, embed this into the product space, and get overall the corresponding vector from the product space with the volume and the trace operation stored. Yeah, so the that's kind of what this embedding does. Okay, and then with that we can now set up. Yeah, sure.
Just go back to the slide.
Yes.
So the trace operator creates a new finite element space.
No, it's there. It maps to that finite element space, but the space is already there. So
okay.
we've.
So it has like the old degree of freedom indices on those boundaries from BT.
Yes, it has the degrees of. No, it's a different space.
So from input L2 finite element space, output facet finite element space.
Okay. So it is a new finite element space. Or a different.
It
No.
Create the finite element space object. The object was there.
Okay. Alright. So it's still connected to the base space. It's still connected to the input space. Well, it depends on it.
Yeah.
So this was crashing anyway, so we had time for this discussion. So let's see that I repeat everything that we need here. No, too fast.
I'm struggling to understand why the trace has to take both the values from either side anyway, right? So why is it more efficient than doing the other?
Because later on when you apply this, you don't have to take a look at both volume elements. You only can do this, you only have the local one element and the facet. The
trace is computing the average.
Yeah, sorry, yes.
Yeah, so you would think the trace needs to look up the other element.
Until it computes it, and then it's got it.
The input is an L2 finite element function. The output is a facet finite element function. And the operation is taking averages from both sides.
Okay.
This trace operator provides us a matrix doing this averaging. So first you do the trace, and in the second step you can use the facet boundary values now on each element.
And referring to Sean, so here we set up the facet FE space explicitly. Yeah? So this is the facet FE space that we use. It has the same order as the L2 space, and has a concrete basis and everything that you expect. So it's not hidden somewhere. Yeah? So the trace operator now is the mapping from VT to VF. Yeah? So that's what you have explicitly here. Okay. So let's hope that it doesn't crash again. So that's where we were. So now we have the volume part C1. We have C2. This is the boundary part, which now takes the volume part and the facet part, and kind of gives us something tested with a volume test function. And that's why we now put on the right hand side the embedding first. So this embedding V takes the volume part, makes it a mix, so it's a product guy of volume and the corresponding trace thing, and so that we can apply the C2 part again to get the convection operator. Okay, that's what we do here. So let's take a look at the timing. Reference was something like 11 or something seconds, I guess. So okay, it's not much improved. Now we do another trick, and the idea here is that we want to get rid of geometry information in a sense. Yeah, so we can do the following trick. So if the velocity is Payola transformed, yeah, so this is kind of what we have here now. So if the velocity has a representation on the reference element such that the velocity is exactly the Payola mapping of the velocity on the reference element, then we have this identity here. So then the volume part, or actually all the other parts as well, so the convection integral parts, they can be represented by corresponding ones on the reference element. Okay, and this allows us to kind of to reduce the configuration that one needs to consider. Okay, and for that, we first of all make sure that we have a Payola transformed velocity, and this we do, for example, by using this HDiff space, which uses Payola transformation for that. There would be other ways to do this, but we'll come to that later. So here now the idea is that we have now a valinear form, and we have this new flag geometry free, which says that indeed the integrals that we have here, they are the same as integrals on the reference element instead of really the physical elements. Okay, this is something that we do for C1 and C2. This is true for both cases. So this, apart from that, it's the same type of integrals that we saw before. And now we do the same trick as before and take a look at the timings. And it should be done by now, approximately. Yeah, so it's 5 seconds, so it's now much faster than before. And of course, you can also tweak the numbers if you make the problem a bit larger. So finally, we also discussed the task manager, so the thread parallel stuff, and we can try if this also improves the speed a bit. So yeah, it's even 1/2 more. So this is kind of how we went from 15 seconds to 2.5 seconds approximately with some tricks. Okay, questions? There's also, you're going to talk the CUDA stuff for tomorrow?
Yes.
Yeah, so there's also something that you can do with GPUs to even improve upon on that. All right, question? Good. Then the last minutes. Let's see. So there's the 352 unit that I just want to advertise. So for the linear case, acoustic wave propagation, you can also do this with getting even a bit more tuning possible, because then you have linear terms and you have don't even have the velocity, the wind in there, so it makes the preparation that you can do for the operator application even more efficient. Okay, then I'm a bit hesitant if I should really start another unit. I don't know. Otherwise, what we did, sir. I don't know.
Everyone is free to leave if they want.
Yeah. So okay. So then let me also just discuss. This is a larger unit, but okay. So I want to give some ideas at least. So let me also just give a few ideas on what we skip here. So there's a unit on surface PDEs with hybrid DG on surfaces. So if you're interested, take a look at this. There's also something where you have the kind of the DG for hyperbolic conservation laws, also time-dependent problems, where the discussion of formulating things as hyperbolic conservation laws is discussed. Okay, and the unit that I want to do now, I want to discuss Navier-Stokes again, but with a focus on operator splitting. So the idea here is that we have a PDE of that form, so the UDT plus one operator AU plus another operator CU equals to 0. And we want to treat the AU and the CU differently. And we think here about Navier-Stokes, with A being the Stokes operator and C being the convection operator. As a convection operator is not very stiff, so we could hope for applying explicit time stepping schemes for that. While for the operator A, we have even a constraint, algebraic constraint, so we want to do something implicit for that. So the idea is that we do an operator splitting of this form, so that we have an explicit time discretization scheme for the first step, which operates on the convective part, and then we have an implicit scheme for the second one. And here we also want to do something for the explicit part, or for the implicit part, we want to do something related to hybrid TG. Because when it comes to solving linear systems, hybrid TG is quite a good idea. However, when we don't have to solve linear systems, then there is no need for hybrid TG. Here we want to do rather standard DG discretizations. So here now the idea is not only to distinguish A and U in terms of the time discretization, but also in terms of the spatial discretization, and to kind of combine this properly. Okay, what we do here is we use our favorite space for velocities, an HDiff conforming method. But HDiff conformity for Navier-Stokes does not suffice because you have viscosity, so you also have tangential continuity to apply for. So that's why we have also a DG or hybrid DG part taking care of the tangential continuity in your variation formulation. However, for the convection, we want to do standard upwinding, so what we did in the previous unit as well. Now we'll take a look at the standard problem that you saw before, so that the Schaefer-Turek benchmark here flow around the cylinder. Okay, so this is the geometry. Not draw this. So so for the Stokes discretization, we use a HDiff conforming BDM element on each element. We use a vector facet IV space, so a facet space just for the tangential component. This is something that you get with ngSolve. So the degrees of freedoms are kind of indicated here. So you have a normal continuity because in the HDiff conforming space you have tangential continuity. You do not have tangential continuity anymore, so it's not there. And we introduce now this facet space to do the non-conforming coupling in a not as expensive way as standard DG has. Okay, so this is kind of what we want to do here. The vector facet is old style. It could be updated anyhow. So this is kind of what you have there. Let me be a bit brief on this. So this is now the Stokes, the viscosity part, and the corresponding pressure and divergence free constraint in one form. So this is KH bilinear form. Note that here we now have jump terms, but as normal continuity is given in the space, the jumps are only tangential jumps. Okay, and this is kind of how you can set this up in ngSolve, so nothing surprising here. It's of course element boundary integrals because it's hybridized, so there's no coupling from one element to the other apart from the usual degrees of freedoms that you have on one element. Okay, so we also have a mass matrix on this Stokes space. We solve the initial conditions by essentially inverting this Stokes operator part. So this is kind of what you also saw before. So this is a Stokes solution on the Schaefer-Turek geometry. So somehow this is all screwed up. But now we have the other part. So this is essentially now the preparation for the implicit step part. Now you want to do the convection application. Oh shit. What we need now is operations transferring information from the one space, let's say from the Stokes space, so from the space from this HDG space to just a standard vector valued DG space and back. Okay. So here's kind of what we can do. We do this in terms of mixed bilinear forms. And kind of in the supplementary, you will see that there's even more elegant ways to do this. But here again, this is kind of what we saw before. We have a matrix, a bilinear form. We use this non-assemble flag, so we have an operator of the corresponding with the corresponding actions. And what we do here now is what we saw before. We have the convection as before with all the integrals. So this is now vector value, but apart from this is exactly what we had before. We have the convection operator in L2. So the tricky part is now in in combining the hybrid and the DG part. Okay, and this is what we have here. So now we define a propagation operator, and the idea is that we first take a solution from the hybrid DG Stokes space. We convert this into an L2 function in the representation of the standard L2, and then we do several time steps on that with the convection operator only, and then we map back to the Stokes space again. Okay, and this is now, we do this with a linear operator that we define ourselves, so that's also what we saw before. So what we need to implement is essentially the multiplication operation. Okay, so what we start with is the input is x, is the vector from corresponding to the product space of the Stokes problem. But now we have this BF mix, so the mixed mass matrix, which essentially converts this into a functional in the L2 space, and now inverting the mass matrix in L2 space gives us a representation as an L2 function. So this is what you have here. So you have an L2 function, or the same kind of representation of the underlying HDiff function now as an L2 function. Okay, and then we have the application of the convection operator, the inverse of the mass matrix again, times time stepping. So here this is the standard explicit Euler time stepping now for several substeps that I do within one of these propagation steps. And then afterwards I map this back to a functional over HDiff. So this is kind of the transpose of this mixed mass matrix operation. Okay, and this is kind of what the Stokes part still missing is essentially then what we also saw for the parabolic problem, the M star matrix, so the Stokes operation times delta t plus the mass matrix, and then taking the inverse of that. Okay, and now what do we essentially do in the loop below? We have the propagation operator that we defined before, and now we do exactly, we take the old state, we subtract the M star matrix. Here we kind of do the propagation operator, do the inverse of this M star Stokes operation, and this is one time step essentially. Yeah? So the convection operator operations, so the sub stepping is part of this convection operator application, and the remainder is just solving kind of the unsteady Stokes problem here. Okay, so that's kind of what we can do, and yeah, what you see is kind of now the nice animation of that. Okay. Okay, I think I'll leave it with that. Just a short kind of, I think you can optimize this. So there's already something called the convert L2 operator, where you can directly, without this mixed bilinear forms, you can more directly do the corresponding embedding, corresponding mapping in ngSolve. Okay, questions? Okay, if not, then I think I'll stop here. Yeah, okay. All right. And I don't know if there's some final
there was at some point in the program that there was a no-host social gathering today.